Hello everyone at day 3 of DevCon24. We are here in our studio in Brno, Czech Republic, where the European office of Espressif System is located. I'm Sergey, a software manager here at Espressif.
And I'm Sudeep, an embedded software developer here at Espressif. It's been an absolute blast hosting this conference for the past 2 days, and I'm thrilled to join you again here on the final day of Espressif DevCon24.
It's hard to believe that we are already on day 3. The past 2 days have been jam-packed with exciting talks and keynotes. Let's take a quick look back at what we have covered so far.
Right, on day 1, we had our founder and CEO Theo Suyan give us a sneak peek at some of the exciting new hardware and software developments happening at Espressif. And then we heard several talented Espressif engineers covering a range of aspects about Espressif platforms. From IDEs, to new peripherals, to Zephyr, to security, we covered it all.
And yesterday's program was equally wide. First keynote made by our VP of software Ivan Grohodkov explored details of ESP-ITF build system. We had exciting talks given not only by Espressifers, but also by our wonderful community members and customers. Topics covered were as wide as graphical interfaces, web RTOS, AI agents for electronics, and encryption. If you missed any of these, you could find links in our YouTube channel or at devcon.espressif.com.
And today we are here at day 3, where we will be showcasing some of the brilliant projects that have come from our very own Espressif community. Today there will be a total of 9 talks of around 30 minutes each, followed by a 5-minute live Q&A. And be sure to stay engaged in the live chat and ask your questions or post comments, and we will answer some of them right here. And do not forget that at the end of the day, we will have an extended Q&A session where we will try to cover all remaining questions that have come through the DevCon all 3 days.
Let me remind you to like this stream and subscribe to our YouTube channel. There is also a feedback forum. Leave your comments and suggestions and you may win a dev kit. What do you think, Sudeep? Should we keep everybody waiting, or we can introduce our first speaker of today?
No, let's do it, Sergey. Our first keynote speaker of the day is Juraj Michalek from Espressif. He's an expert in embedded systems with years of experience of making life easier for developers. If you've ever felt like you're getting lost in the woods of embedded development, or you've faced those hidden traps that are slowing you down, then this talk is for you.
So, welcome Juraj with our keynote stuffed with practical tips, tricks and techniques for embedded developers.
Hello and welcome to the third day of Espressif Developer Conference. I am very excited to welcome you here, and we at Espressif are happy to be part of such vibrant community of developers, both enthusiasts and professionals. So let's explore the world of ESP32 today. In early days of Espressif, if you ask me which chip to choose, the answer will be simple. It would be just ESP8266. Since those days, many new chips were developed and are available on the market. For a beginner, it might be quite confusing which chip to choose. So let me give you some guidance. Let's start with ESP32S3. ESP32S3 is part of this ESP32S3 box 3, and it allows additional PSRAM, so it's suitable also for project that requires GUI. It's also part of other development kits like M5 Stack Core S3. But what if your solution is battery operated? In that case, I would go for ESP32C6, which has support for Wi-Fi 6 and has low power core, which is using very low current. But as you can see, there are many more chips available. So how to choose from them? Our team at Espressif put together product selector available at products.espressif.com. Let's explore Product Selector. Let's navigate to espressif.com, Hardware and Product Selector. On the left side, we can see different features that we can use for filtering, and you can choose for your project, like Wi-Fi support, Bluetooth support, Thread and Zigbee support. There is also marketing status, which indicates whether the chip is produced and available on the market, like the mass production, or whether the chip was phased out and is no longer available, like EOL, means end of life. So let's select ESP32S3. Here you can find more details about the chips, like memories, voltage, communication interfaces, security features, and temperature range. You can use also further links like documentation and certification or development kits. Product Selector has also support for comparison. Let's click here and let's compare two chips. In our case, we were talking about the S3, and let's compare it with C6. Now we can see the difference between those chips. This tool can help you to navigate through different offerings and help you to find correct chip for your project. Now we know how to choose the chip, but we will need far more information to start working with ESP32. Let me introduce you to the Developer Portal available at developer.espressif.com. The Developer Portal is available as a GitHub repo, so we invite community to contribute. So should you have an article, tutorial or workshop, please create a pull request. Let me show you how Developer Portal looks like. Let's go to developer.espressif.com. Here you can find Developer Portal. In the blog section, you can find several blog posts about various topics related to ESP32, ESP-IDF. You can find here even an article about coffee machine connected to the cloud using Rainmaker. If you'd like to contribute, the contribution guide is here. The document will guide you through all the questions and steps to creating the article. Adding new article is quite easy. Just fork the repository and then inside content, blog, create a directory, and here you can use index markdown, which contains your article. So you write your article in the markdown format, and then after creating a pull request, it's merged to the main portal and published using the Hugo framework to the developer.espressif.com. Be welcome contributions. Developer community is amazing at sharing knowledge. If you ask me about the tip that I learned from the community, I would definitely pick the video from Andreas Spies, the guy with the Swiss accent, and the video would be about the wire wrap. This simple tool that has been around for decades can really simplify the way how to prototype and how to create projects. So let me show you how it works. Let's connect this red wire to the board, to the pin. So let's strip the wire, like this one. Now we can put it inside the wire wrap tool, put it into the pin, rotate, and it's holding. Now we can test whether it works. Yes, it's working. Now we can remove the wire. Just rotate the tool and rotate in opposite direction. As you can see, the wire was removed. And now we can test whether it's working. Yeah, it's not working. Let's switch from real wires to virtual wires. Thanks to simulator like Walkway, it's possible to simulate ESP32 or even ESP32P4 in the web browser or IDE or continuous integration system. Today we will hear the talk about the Walkway. Let me give you a sneak and peek. Let's open Walkway at walkway.com/ESP32. Here we can see featured projects created by community, also some starter templates and IDF templates. Let's select M5 Stack Core S3 and run the simulation. The simulation is running. Let's talk about programming languages and technologies. First, we need to mention Arduino, which has huge community. It's well adopted on ESP32 chips. You can find many projects on GitHub and in open source world. So let's see how the Arduino works. Here we have Arduino IDE 2.3. We have selected ESP32S3 box as our target, and here is the Arduino code. We just print the hello and then tic-tac. So let's build the example and upload it to the board. Now compilation is done. Okay, firmware was written, so let's use the serial monitor. Should we connect and we can see hello ESP32 tic-tac. Wonderful, so it's working. Now let's talk about C and C++. Here the choice is ESP-IDF framework. ESP-IDF is well supported on all ESP chips and can be used to develop professional projects. So majority of IoT solutions out there are using ESP-IDF. So let's take a closer look how the build of ESP-IDF project looks like. So let's build ESP-IDF project. This one is located in examples, get started, hello world. First, let's make sure that we sourced ESP-IDF. So we can do it by running this command. Now we can set the target. Since we are working with ESP32, it will be ESP-IDF, set the target, ESP32S3. And now we can type IDF py build flash monitor. Very well, now it's flashing. And as we can see, the example in ESP-IDF is working. Popularity of Rust programming language has been growing over past years. There is great community of developers, and ESP32 chips are well supported, both in Rust STD, building on top of ESP-IDF, and Rust non-STD, also known as bare metal. So it's up to you to choose whether to build on top of C framework or use pure Rust implementation with Rust bare metal. So let me show you how the build process looks like. To build a Rust project, we will use cargo command. So let's type cargo run -- release. We recommend to use -- release profile so the binary is smaller and execution on the MCU is faster. As you can see, Rust is compiling, and Rust produces binary which can be flashed to the chip. Now we can choose the device and press enter. And the flashing process is using ESP Flash tool, which is also written in Rust. And here we can see the working application. Arduino, C++ on top of ESP-IDF, Rust. There are more programming languages that you can use with ESP32. So let's mention a few of them, like Python-based programming languages, MicroPython, or the Adafruit version of CircuitPython, both with great communities. Let's mention also Swift, that was announced during WWDC 2024. And also let's mention Zig, which is gaining popularity recently. And there are many more. Until this point, we were talking about programming languages and technologies. What about operating system? In case of ESP-IDF, there is free RTOS underneath the whole framework. In case of bare metal, there is nothing, there is just bare metal. What about other operating system available for ESP32? Well, there is NATix. NATix is very Linux-like system. You can write applications in many programming languages on top of it. Then we definitely need to mention Zephyr, which gained popularity in the industry and makes it easier to port applications between different embedded hardware. So definitely you can check also these operating systems. I'd like to take a moment and thank community for great effort and for creating many interesting open source projects. And thanks to cooperation with Electr magazine, we were able to create a dedicated issue just to ESP32. So this is the issue December, January 2024. You can find here many ESP32 based projects. So Elector is a great source of information about ESP and new things that we are releasing. As we are exploring these programming languages and technologies, I encourage you to take a time, learn a new technology, and please, should you find something interesting, create a pull request to our developer portal and help us grow the knowledge available to the community. I wish you great experience at the third day of Espressif Developer Conference.
Thanks, Uri, for those invaluable insights about boosting productivity in embedded development. I'm sure many of us are already thinking about how to apply these techniques in our work.
Absolutely, Sudeep. Speaking of productivity and making life easier for developers, our next speaker is someone who truly believes the power of simulation to change the way we develop and test embedded systems.
That's right. Up next, we have Uri Shaket, a renowned maker and an expert in the field of IoT and embedded systems. Uri is going to talk about simulation and how it can become your superpower, help you develop faster, debug harder, and test stronger.
Uri will show us how virtual hardware platforms like Walkwe can transform the way we approach development of embedded systems. Over to you, Uri.
This has to be magic! Hi, I'm Uri, the creator of Walkwe and also the co-founder of Tiny Tapeout. So what's Walkwe? It's the world's most advanced ESP32 simulator. It works in VS Code, in JetBrains, in your browser, and even in your CI/CD pipeline. We are going to see some real-life examples of using Walkwe, learn how to set it up for your projects, and explore some of the more advanced features such as Wi-Fi simulation, CI/CD scenarios, and custom chips. Let's dive in! Go to walkwe.com, click on ESP32. We have a big bunch of examples here, or we can start from scratch. You can see we have the ESP32 family of dev kits and some third-party boards like the S3 box or M5 stack. And we can write code in Arduino, MicroPython, or even use ESP-IDF code if you are feeling adventurous. Now, let's see some example. I like this one, the joke machine. I click on it. On the left, we see the source code. This is Arduino code. And on the right, we see the diagram with all the connections. And all we need to do, just press play to start the simulation. And now it's connecting to the virtual Wi-Fi. It will get an IP address in a moment, connect to the joke HTTP API server, and no, I'm not going to read this one out loud. Now let's go back and see another example. This time it's a MicroPython example, and this is going to connect to an MQTT broker and report the temperature from this DHT22 sensor. So first of all, before running it, let's open this web-based MQTT client, put them side by side, adjust the size of the window, and let's get this MQTT client connected to the same MQTT broker as this MicroPython code is going to connect to. So we are connected. And now let's subscribe for this topic. It says here in the instructions, Walkwe weather. You can see that the code also uses the same topic name to publish the MQTT messages. So I'm going to add a subscription, subscribe, and start a simulation. And now the MicroPython code is running and it's going to connect to the Wi-Fi. It's connected to the MQTT server and we can see the message. And if I click on the sensor, I can change the temperature and you can see the messages coming from MicroPython right into the MQTT broker. And if I want to go back to MicroPython, I can just click Ctrl+C and start interacting with the REPL. Like, let's see what we have in this sensor object. We can see we have all these members like sensor.pin that tells us which pins the sensor is connected to. And we can take another measurement and print sensor.temperature or just greet hello ESP DevCon. Yeah. So far we have seen two client examples, an HTTP API client and an MQTT client. The next one is actually going to be an HTTP server running on the simulated ESP32 and controlling two LEDs. Let's read the instructions. So first of all, we need the Walkway IoT gateway. It's a small app that allows the computer or the browser to connect into the simulation, into the HTTP server. And you can see all the instructions here. It's a paid feature. And I'm already running it on my machine. So we can just go back and press play to start the simulation. And it tells us we need to open this link. Let's go back into side-by-side view, open the link, and voila. This is the web page that you can see here, the source code for this web page served from the ESP32. And we can click to turn on and off each of the LEDs. And if we scroll down a bit, we can actually find here this code that handles the toggling of the LEDs. It listens on the /toggle URL, and then depending on the LED the index of the LED that it gets from the path, like this is LED number 2, it just toggles the state of the LED. If we refresh the page, we can see it actually toggles it on each refresh. Now, do you see this little Wi-Fi icon here? It shows you the connection status, but when you click on it, you can uncover one of the more powerful features of the simulation, downloading the Wi-Fi packet capture, aka pickup file. When we click on it, we get a file that we can open in Wireshark, and then we can see all the Wi-Fi traffic that went through the virtual access point during the simulation. We can see the Wi-Fi beacon advertisement. So Walkway Guest is the name of the virtual access point that we have in the simulation. And if we go down, we can see the Wi-Fi association and then the DHCP negotiation where the ESP32 gets its IP address. And further down, we can see the HTTP request and the responses. And if we right click and follow HTTP stream, we can see the request that my Chrome browser sent and the response that we got from the ESP32 HTTP server. This feature comes really handy when you need to debug connectivity or protocol level issues. Okay, let's go back to the browser. One thing I want to show you, when you click on the ESP32, there is this question mark. It takes you right to the documentation. And if you scroll down, you can go to simulation features and you can see all the simulated ESP chips and which features and peripherals we simulate. So PSRAM, UART, USB, some are not yet supported, but we are working on them. And speaking of documentation, if you ever forget how to connect to the virtual Wi-Fi, just go to the ESP32 Wi-Fi guide, where you have the name of the virtual access point, the channel, and you can also see the IP address and the MAC address of the simulated ESP32. Up to this point, we have seen 3 IoT simulation examples, and they all run in the browser. Now, this is great if you want to quickly prototype something or you want to share your project with friends or colleagues. And it's also great for classrooms and workshops and other educational use cases. But what if you want to work locally and use your favorite development tools like Git and your favorite IDE? Enter Walkway for VS Code. Let's start with a quick example. This is a project using LVGL ESP IDF project, and it just displays, scrolls some text on an OLED display. Now it's already set up for Walkway, so if we click on diagram.json, we can see the ESP32C3, the connections, and the OLED display. And all we have to do is just click play to start the simulation. And we can see this terminal window with all the output from the boot ROM and the log messages from the application. And then on top, we can see this text scrolling. Now, let's say we want to make a change to this code, so we can open the code side by side with the simulator. Let's put the code on the left, the simulator on the right, and then let's change this text to say, hello, Espressif DevCon24, and save, recompile the code. and it's now, no, not flashy, just recompile it. And now it's rebuilding the code. It will take a few moments to recompile this code, and Walkway actually monitors the binary, and voila, it found that we updated the binary, and we get immediately to see the new code running. No need to wait for flashing. Our friends at Espressif even coined a term for this, Walkway style of development. So even when they develop on the physical device, they still use Walkway to test their changes while they are waiting for the firmware to flash. Alright, let's explore the debugger now. I'm going to set a breakpoint here in the loop, press F1 and start Walkway in debug mode. And this starts the simulation. And now I need to press F5. Let's put the simulator side by side with the code first. We need to keep it visible while we are debugging. And now I'm going to set F5. This will tell VS Code to start the debugging session. It takes a few seconds and we can see the debugging session has started. And we hit a breakpoint. Yay! Now, do you see these labels next to the pins? We call this feature pin dump, and it appears whenever you pause the simulation, even without using the debugger. This is very useful to spot connection errors or misconfigured pins. And for instance, we can see here that pin 3 is set to Espressif SDA. It actually is connected to the SDA of the OLED. Pin 4 is set to SCL, and pins 5 through 7 are configured for JTAG debugging. Well, back to the breakpoint. We can step through the loop and see the display updating as we go. We can see the counter going up as we step through the loop. We can also inspect the variables. For instance, this label, this uptime label, we can see it here. We can take a look at the coordinates X, Y, and we can even cheat the uptime here on the right side and bump it up, let's say, to 1000, and then continue the simulation to see it updating here, 1001. On the right side panel, we can also see the call stack. And if we want to dig deeper, we can even take a look at the CPU registers, or go to this memory dump and see the contents of the ESP32 memory. And there is my favorite, this peripheral viewer lets you take a look at the peripheral registers, like for instance, the I2C, where are you? I2C registers. You can read all of the registers, the interrupt status, and I like this one, the RNG, because every time it returns new random generated value. One of the best things about debugging with Walkway is the number of breakpoints that you can have. On the real ESP32, you can have up to 2 hardware breakpoints and 2 hardware watch points. And with Walkway, there is no limit. You can have as many as you want. Yeah, that's right, as many as you want. Now, let's see how you can add Walkway simulation to an existing project. We'll take the Hello World example from ESP-IDF and see how to quickly set up for simulation. First, we are going to install the Walkway command line tool that is going to help us set up the project. There is a command for Linux, and I will copy the second one for Windows PowerShell. Go to my command line, paste the command, and bam! I got a CLI, it's installed. Let's go to VS Code. This is the Hello World example from the IDF, and I already built it with idf.py. Now, all I need to do is just, let's clear the screen, type Walkway CLI init, and it runs. It detects that this is an ESP-IDF project, so all I need to do is to select the board. In this case, I built it for the C3, so I will choose the C3 dev kit. Go ahead with the default firmware and ELF file location, and that's it, ready to simulate. The CLI did 2 things. It created this diagram JSON file with the dev kit, the C3 dev kit as we told it, and also this walkway.toml configuration file. This file tells Walkway where to find your firmware, and check this link for more options like TCP port forwarding, which is useful for the ESP32 web server that we saw before. Let's see another ESP-IDF example. This one is generic GPIO. It configures 4 GPIO pins, 2 as outputs and 2 as inputs with interrupts. And we will be using the C3, so these are the pin assignments. Outputs are 18 and 19s, and the inputs are GPIOs 4 and 5. I've already run WalkWe CLI init, so we can jump straight into editing this diagram. Let's add 2 buttons for the inputs 4 and 5 and press D to duplicate it, 2 to set it to blue, 1 connects to 5, 1 connects to 4, and these are pulled up the inputs, so we will connect the other side of each button to ground. Press A to add an LED and flip it, set it to green, duplicate it with D, set it to blue, connect the top one to 18, the bottom one to 19, and let's ground both of them. So the first one goes ground, the second one goes ground. Save and simulate. And now the LEDs are blinking, that's probably expected. Let's test the buttons. That's weird, when I click off them, there are a ton of messages in the terminal. Let's take a look at the source code. This is the GPIO interrupt handler. We can see that for each generated interrupts, it queues an event. And then we have this GPIO task that pulls events from the queue and prints this message for every event. So for each interrupt, we expect to get a single message, but we get many. Let's try to figure it out. First of all, pause the simulation, and we can see that pins 5 and 4 are configured as inputs with pull-ups, 18 and 19 as outputs, as we expect, so it's probably not a pin configuration issue. We are going to use another powerful debugging tool, the virtual logic analyzer. It's going to show us the signals that go on the wires, so pin 5, pin 4, and also the URTX, and ground is optional, but let's get it connected as well. Start a simulation, click on this button, and we can see that it collected a few samples, and then click the other button. And when we stop the simulation, it will ask us where to save this file with the recorded signals. Click Save. We can open the recording with a free software called PulseView, and we can see the 3 channels that we recorded. This one is IO5, IO4, and the TX of the UART. And now I want to show you a cool feature of PulseView. So there is this analyzer's pane, and we can actually get it to decode the UART. So if we type UART, we add a UART analyzer, it automatically detected the TX channel, and we want to display it in ASCII. And if we zoom in, we can actually see the data that was transmitted, like GPIO5 inter value. And if we look at this, we can see that we had multiple messages. And if we zoom at the IO5, we can actually now see the reason why. The problem was that when we clicked on the button, the signal was bouncing here, and we can see that we also had it bounce when we released the button. This can explain why we had multiple interrupts on each click. Let's go back to the simulation, click on the buttons, disable the bouncing behavior, and test it again. Now when we click on the green button, we only get a single interrupt message, as expected. The virtual logic analyzer helped us spot the problem real quick. And if you are curious about the button bouncing behavior, check out the documentation. We have seen WalkWe running in the browser, in VS Code, and now I want to show you a third way of using WalkWe from the command line. We'll use the WalkWe CLI, the same one that we installed before, but first we need to generate a token. We'll click on the link, create a new token through the web UI, give it a name, EDC token, and we are using Windows, so we will copy this one and paste it into the command line. Now we can run the simulation and we see the output coming to the console. So what makes this useful? Testing automation. At a basic level, we can tell the CLI to wait for a specific string like CNT2. And this is all we need to do for a simple test case that we can now run on every commit. Yay, test passed. Now, let's see how to take testing to the next level using a feature called automation scenarios. Each scenario is a YAML file that breaks down the test into a series of steps. We'll start with this example from the documentation and adapt it for our project. Let's call it buttons scenario.yaml, paste the content, give it a name, test button press. My name is Uri, and now we should define the list of steps. So first of all, we got a good example here. We want to press the button, but we first want to make sure that this CNT0 is displayed before we press the button. So we will add a wait serial step to wait for CNT0. Let's run again the simulation in VS Code to go through the flow that we want to test. First, we need to find the ID of the green button. We can see it when we move the mouse over one of the pins, that's BTN1. And when we click on the pin, we expect to get this string here. Let's copy this and go back to the YAML file. And now we have enough information to complete the scenario. Let's paste here the string that we expect after pressing the button. And the example code we copied already presses the button, but for the good measures, let's also release it, unpress it. BTN1, that's the green button, and we will wait 100 milliseconds between pressing it and releasing it by setting the pressed control to 0. And that's it. The scenario is ready and we can run it. WOCWI CLI -scenario button.scenario.yaml. Wait a few seconds for the simulation to complete, and it worked! Scenario completed successfully. We can also use WOCWI together with PyTest Embedded, the embedded testing framework from Espressif. And this project, like many other ESP-IDF examples, already comes with some test case that expects the text CNT and some number to appear in the output. If we wanted to run this test on a physical device, we could write PyTest with target ESP32C3, but that of course won't work because I don't have the board plugged into my PC right now. Instead, I could just run the same PyTest command with -- embedded services IDF and WOCWI. And that's all we need to do in order to run the same test in WOCWI. This setup with PyTest makes it very simple to switch between testing on the physical device and testing in simulation in WOCWI. Alright, this is CI time! I'm going to show you how to set up WOCWI inside GitHub Actions. Let's start! I've already pushed our project to GitHub, so we need to set up the WOCWI token first. We go to Settings, Secrets, Actions, and we create a new repository secret. We call it WOCWI CLI token. And then for the secret itself, we can copy it from the same dashboard that we did with the WOCWI CLI. Here I still have this open. We can copy it, paste it here, and add secret. Now we will switch to VS Code, create the workflow file, GitHub workflow, and we'll call it build test.yaml. I'll ask Copilot for help because I'm too lazy to write it from scratch, so GitHub workflow that compiles ESP-IDF project on every commit and dispatch. The LLM is working its magic. Accept. Not too bad. Let's bump checkout to V4. And this step should be ESP-IDF CI action. And we'll call it build project. And to build it, we need to tell it the target, ESP32C3, and we don't need those. Instead, let's add a step to test with WOCWI. We are going to use the WOCWI CI action at version 1, and it requires a token. So let's give it the token that we put in the secret. That should be WOCWI CLI token. That's how we called it. And we also need to tell it which scenario file to use. So that's the button.scenario.yaml. Save, commit, CI, build and test in WOCWI. Push, and let's see if we got it right. Let's go back to GitHub, switch to the Actions tab. Oh well, it's compiling, so I'll be right back. Back with some good old Dinoti. Let's check up on GitHub. Great, it's green. Let's click and see the details. So we can see it took about 2 minutes to build a project with the ESP-IDF, and then 6 more seconds to test it with WOCWI. And if we open this step, we can see that it first installed the WOCWI CLI, then it ran the WOCWI CLI similar to what we did in the VS Code terminal, and it ran the scenario, and scenario completed successfully. Now let's make this project even more interesting and add a second chip into the mix. First, we'll rename the existing diagram to diagram.esp32c3.json, and then we can use WOCWI CLI init again to create a second diagram. Yes, I'm fine, and this time we'll choose the ESP32c6, and we got a second diagram JSON. Let's rename this one into diagram.esp32c6. Close the terminal, and now we need to copy the buttons. We can also copy the LEDs from the old diagram, Ctrl-C, to the C6, the new one, Ctrl-V, and let's get the buttons connected. So the green one goes to pin number 5, and then the blue one will go to pin number 4, and we can leave the LEDs disconnected for this demo, so let's just connect the grounds, save, and go back to the build test YAML file. We'll configure test metrics. This will tell GitHub to run our test each time with a different value for the target. So once for ESP32C3 and once for ESP32C6. And also set fail fast to false, so all the tests keep running to completion even if some of them fail. And now we can use this target parameter from the metrics in our steps. So let's just use the matrix.target here. And also for the diagram file, we are going to use diagram.matrix.target.json. And that's it. We are good to go. Save, CI add ESP32C6, push, and back to GitHub. We can see that it's now running both jobs in parallel for the C3 and C6, so I guess it's time to take another sip of the Dino tea. 2 minutes later and all green. And this is how you can run many tests in parallel on multiple virtual boards. We call this walkway in the loop testing. And now for some real-world examples. Our friends at Espressif use walkway to test their ESP32 Arduino core on every single commit. They run the tests on all the supported ESP32 chips using PyTest Embedded and the Unity framework. This way, they can immediately catch any regressions when they make changes or when someone from the community sends a pull request. If you are curious, you can find the actual test code in the repo under Tests Validation. We can see that they have a similar setup to what we did with one diagram file per chip, as well as a scenario file that pushes a button. Another great example is this ESP32 Spooky Maze game. Spooky Maze was built by Raimi Kalek from the Espressif Rust team to showcase the capabilities of embedded Rust on ESP32. Here, he has a GitHub action that uses walkway CLI to take a screenshot automatically and save it to a PNG file. And if we go to the Actions tab, we can see there the screenshot from the simulated LCD display. Those screenshots are really useful for visual validation of your embedded user interface. And now I'm going to show you how we use walkway to test walkway. We have this ESP32 test binaries repo, and it contains many precompiled test binaries from the ESP IDF, like these UART or I2C drivers, crypto accelerators, PSRAM, Wi-Fi, etc. For each of those test apps, we have a test scenario file, and we are running all those tests on a daily basis. Let's take a look at the Actions tab and see the results. Most are green, but we can see that a few days ago we actually had a regression. If we look inside, we can see a matrix with all the chips and all the tests that we run, over 150 tests in total, and we can quickly spot the test that failed. In this case, some changes to the ESP Wi-Fi driver caused incompatibility with the simulation. Thanks to this automated setup, we were able to quickly spot the issue and fix it the next day. If you want to set up a walkway GitHub action for your own embedded project, you can simply copy this snippet from the documentation. You can also find more examples, some of them include automation scenarios, as well as a blog post showing how to use walkway together with Platform.io to set up CI. Alternatively, if you want a complete ready-made setup for ESP IDF with PyTest Embedded, take a look at Espressif GitHub ESP test template. This template already includes CI configuration for walkway in the loop and even optional hardware in the loop testing in case that you need it. One question that I frequently get is, what happens if the sensor or display that I want to simulate does not yet exist in walkway? In that case, you can create it yourself using the Custom Chips API. To get started, go to Walkway Online, select the Custom Chip option, then type a name like LM75A, a digital I2C temperature sensor. Then define the pinout, and finally write C code to implement the logic of the simulation model. I think we have had enough content for today, so I'm not going to cover the specifics of the custom chips API, but if you ever need it, there is extensive documentation, and there is also a very good video tutorial from Psychogenic Pat.
Hey, I'm going to show you how to implement a custom chip to include in digital simulations using Walkwe from A to Z. And I mean, we'll go through the datasheet.
Well, thanks, Pat. And of course, when you finish writing your custom chips, you can publish them on GitHub and then use them in Walkwe on VS Code and of course in Walkwe for CI. We have been building Walkwe for the past 5 years, but we are not done yet. Let's take a quick look at what's coming up next. First, we keep adding new chips like the ESP32P4, and later this year we are also planning the C5 and the C61. We are also working on the Walkwe viewer that allows you to simulate a firmware binary directly from GitHub. Let's take, for example, this Zephyr project repo from Benjamin Kabe. It contains some precompiled binaries for several Zephyr project demos like this C3 sensor shell. We can simply copy the link to the firmware binary and paste it in the viewer. Same with the diagram. Load project. And voila, the simulation starts immediately in the browser. Let's change the temperature of the sensor to about 40 Celsius and now have some fun with the Zephyr shell, trying to read it back. Sensor get MPU 6050 at 68. Yep, it worked. You can copy the link from your web browser and share it with anyone and they will get the same immediate simulation experience. And if you are like our friends at Adafruit and need more complex Walkwe automations, we are currently working on a new Python client library, so you can use Python to write complex test scenarios. Well, that's been quite a journey. I've spent over 25 hours preparing, recording and editing this talk, so I hope you enjoyed and found it valuable. You can find me on the Walkwe or Tiny Tapeout Discord. Ciao, see you next time!
Hello, everyone, and welcome back to DevCon24. This is the third and last day for this conference, and I hope you are enjoying. My name is Pedro. I'm Developer Relations Manager here at Espressif, and I will be your Q&A host for today. And to join us for this Q&A, I have here Uri. Hello, Uri. How are you?
Hey, I'm doing good. Good to be again on the ESP DevCon. I missed it last year, but now I'm here again.
Yeah, so this is the second time you are participating. Is that right?
Yep.
Yeah. All right. Okay, so thank you so much for your talk. I'm pretty sure that there are a lot of people interested on how to get started with Walkwe, and this presentation will be very handy. So we have here some questions, and let's start with the first one. So what is the performance overhead of simulating complex circuits in Walkwe?
So this is a question I love because the answer is, as usual in programming, it depends. It really depends what we are trying to do. And like most things in computer science, it's a matter of trade-offs. And we decided to take some trade-offs to support the most common use cases. And at the same time, to keep this accurate, I showed during the talk, we have this ESP32 test binaries repo, and we are running the ESP IDF tests on a daily basis. So we want it to be as accurate as possible. But on the other hand, we don't want it to be as slow as possible. So in order to do that, one trick that really speeds up the simulation, we simulate the microcontroller as if the CPU frequency was much lower. So instead, like for the C6, the default CPU frequency is 160 megahertz. And if we had to simulate 160 million operations per second on a modern computer, then that would be slow. It would take more than a second, and we want to achieve real-time performance. So usually we just run the simulation as if the CPU was running at 8 megahertz. And interestingly, you would say it's 20 times, like the difference is 20 times. So how comes it works? Like, it probably doesn't really work this way. Most programs will probably break. But the truth is, most programs don't really care. The timing of the simulation still works well, and most programs just run fine. And if you have a specific program that does need very specific, very accurate timing of the CPU clock, then you can tell Walkway to slow down. But most users don't have to pay the price of like the full clock speed simulation. And we also have some cases where we detect that the code is doing something that is timing sensitive, like controlling neopixels. And only in those cases, we actually speed up the simulated clock to 160 megahertz. So complex circuits can be very slow to simulate, and we just try to throw in the right optimizations and take the trade-offs. So for most users, it runs fast and accurate.
Okay, thank you for the very detailed answer. We have one question here about debugging capabilities. So what debugging capabilities does Walkway offer for developer? And let me extend just a little bit in how Walkway can help developers to debug applications.
So at a very basic level, you can just connect to Walkway with GDB or any other debugger that supports the GDB protocol, such as Visual Studio Code Debugger or JetBrains, and step through the code, read, write, set breakpoints, read, write variables, the memory, interact with the peripheral registers, and also set I think one major difference with the hardware is that you have unlimited number of breakpoints and watch points, whereas in the hardware you have up to 2 hardware breakpoints and I think also 2 watch points. So in that aspect, it brings something extra to the table. But on top of that, and this is something we are looking at right now, there are other things we can do to make the simulator even more useful for debugging. And one thing I think I didn't cover in the talk is the profiler. So you can basically run the entire simulation of your firmware and then get a view where you see all the functions that were called during the lifetime of your program and how much time the CPU spent on each function. So it's useful both if you have performance issues, so you can like see where the CPU is spending most of the time, and also if you have like unexplained behaviors, because it gives you a very top level view of the program. You can quickly see which flows the program has taken without like having to spend a lot of time stepping through the debugger. If it failed somewhere, you can see that some critical function was not called or was called at the wrong time. And another thing we are now looking at and we may add is some kind of peripheral debugger that will let you see which peripherals the program is interacting with at any given moment. We have some use cases internally where this would help to diagnose if there are some missing peripherals in the simulation. You would probably want to know about it and to get notified about it. But if other users have good use cases for this feature, I would love to know. And also there is like the pin dump that shows you the pin configuration, but I think we already covered this in the talk.
All right, so if I understood correctly, it's much more flexible than when you debug the real hardware.
Yes, and I think another cool feature is the fact that it's very easy to reproduce the same results, because on the real hardware, if you have something that depends on external timing, like a click of a button, maybe a menu that when you click on a button, it sometimes jumps 2 entries, or I don't know, resets or something like that. It can be harder to reproduce with real hardware, but with WalkWe, you can just run the same simulation over again and have like complete control over the external factors.
Oh, okay, I see. Thank you. So let's pick one question here from the chat. I have actually two questions from Mike. Are there any peripherals that are not supported with WalkWe? And then thanks. Looks like the one I'm after is only fully supported on H2. I will give it some testing and see how it works on other chips. It will be awesome to have end-to-end testing on place. So both comments from Mike.
Yeah, thanks, Mike. So yeah, I agree it would be awesome. And in terms of peripherals, let's put it down this way. We don't want to support all the peripherals because that's a lot of work. We want to support all the peripherals that people are actually using. So I would love if you write down which peripheral you are after and what is your use case, how you would like to test this peripheral. For some peripherals, we simulate them at the protocol, like at the bit level, like for SPI or for UART. I think we have seen in the talk the logic analyzer where you can see the actual signals. And if you get the UART baud rate wrong, it will behave as if it was on real hardware. And for other peripherals like the USB and the Wi-Fi, we don't go down the wireless, the physical level. We go at the byte level, the protocol level. So the depth of the simulation and whether we support peripheral, it only depends on how many people actually need and want this peripheral. And I would love if you wrote which peripheral you are after, so we can look into it. And that was for the peripherals on the chip. For external peripherals, there are a bunch of supported peripherals, but I think I mentioned it in the talk. There is the custom chips API, and you can add whatever you want. So we don't want you to be limited. We want you to be able to simulate it. If you can imagine it, you can simulate it. That's the goal.
All right. Thank you so much. And Mike, you can continue talking with Uri by chat. And as well, Uri, I'd like to ask you if you can answer some other questions that you might have in the chat, because we are out of time right now. And so I'd like to thank you so much for the answers.
Sure. Maybe one more sentence. So one thing we are working on right now is supporting multiple ESP32s in the same simulation. So if you are interested in that, then we have a Discord server you can join and find me there.
Yeah, please share the link here in the chat.
Good idea.
Yeah. All right. Thanks. And now we go back to the studio.
Thank you, Pedro, and thank you, Uri, for showing us the power of virtual hardware platforms like WalkWe. I'm pretty sure a lot of our viewers will want to try that out for themselves. Sergey, after virtual hardware, I think it's time to bring hardware into the loop, quite literally.
Wow, exactly. And our next speaker, Lechezar Lechev, CEO of Lechev Space, who is going to introduce us to hardware in the loop, or HAL development. This is a technique useful for dealing with complex aerospace projects. Lechezar will show us how they are built and test different MCUs remotely. So let's launch into the world of hardware in the loop with Lechezar Lechev.
Hello everyone and welcome. Today I'm going to tell you about rusty hardware in the loop setup that I have been exploring. This is part 2 of my talks this year, but I'm going to tell you about part 1 in a bit. So first, I would like to say very, very much thank you to the whole Espressif teams. It's not the first time we've been working together, and it's a pleasure, and I'm very honored to be talking about this topic in front of you. Now, I have a small agenda for today. Just an overview of what we're going to talk about. First, I'm going to tell you who am I and why I'm speaking in front of you about this topic. Then I'm going to share about what we're building at the Rust community and what actually Rust is. And of course, the most time we will spend on tooling, how you can actually build such a setup with the current existing tools in the Rust ecosystem. And of course, I'm going to show you how you can remotely flash. Yay! Small demo, but still very applicable to many of our work. And at the end, we're going to talk about like generally conclusion, where the ecosystem is and so on. So the first thing you should know about me is that you definitely need to come and speak with me if you want to build a spaceship. I'm very into aerospace, and I actually started in 2020 because I usually love a challenge, and the aerospace industry provides a lot of challenges, different challenges, extreme environments, very tough regulation and so on. And I really enjoyed that part of it. And I think this is the future just going forward. On most platforms, my name is Lechezar Lechev, but on most platforms, you can find me as LPL, except on X, where I'm with _. If you want to say hi or you want to discuss something, just direct message me or, join in the Discord server that I'm going to share in a bit. Okay, apart from that, I started my own company in a sense of having like a small space for development. And of course, when you are talking about the business, you do have a few disciplines you have to handle. First, you have the technical stuff, of course. As developers or hardware people, we would like to solve an issue, whether it's useful for anyone else. They can decide. But if we find a niche, something that we need, and we can build it, then usually that's enough for us, right? Apart from that, though, you still need to have some kind of a business model, how you're actually going to make money out of it. And of course, apart from the business model and the technical solutions and so on, you do have resources. So resources can be anything from equipment or people and so on. Of course, you have to be sustainable as a business. So you have to find a way to keep doing what you're doing without breaking the bank or without being on the street, basically. Because you don't make money out of it. And as you can see here, like I added this screenshot from my from the sponsorship account in GitHub. But you can see that for 2.5 years, I haven't received a single sponsorship, although I have been contributing to many projects, especially in the embedded world. And this just showcases how challenging this sponsorship kind of a way to sustain your open source work is actually is. And finally, of course, you have to when you're building a product, whether this is a software or a hardware product, you have to define some kind of a scope, right? You can still start working 5 years, 10 years on a single project without validating it, without defining what the people actually want, and hope for the best that when you release it it's going to be very profitable or very used. But that's not usually how we do things, right? We want to start with something small and implement that to validate it. And of course, income, as I said, you have to provide for your family or for yourself, so it's very important to handle that. Apart from these disciplines, when we're talking about aerospace, of course, the technical disciplines or the science part of it is very important. And in aerospace, what you find out is that you basically have all the disciplines you can have, right? From biology to mathematics, and of course, when we're talking about mathematics, It basically comes to everything related to physics, or even like how do you control a given satellite, how do you orientate specifically to Earth, and so on and so forth. So this slide is just more to give you a sense of the vastness of the aerospace industry, because of course in mathematics you can do simulations, you can do fluid dynamics, you can apply mathematics or dynamics on your flying thing, whether it's a rocket or a drone. It really doesn't matter, but mathematics is in the core of things. But then you have all the other things like physics and chemistry and biology. And just again, for a few examples that you can look at, of course, material science, when you're picking, for example, what material to use on your rockets or for a given pressure vessel or whatever, you have to know what the properties are, how the structure will react, and so on. And of course, you have guidance, navigation, and control, having different frames of references for your, let's say, drone or your satellite or your space probe. And you have to convert different things or different coordinate systems, different frames to each other, and so on. So these are just a few examples that I wanted to give you, just to get the sense that in aerospace you cannot know everything. You can partially do everything and know a bit of everything, but you need a big team for handling that. So it's very capital intensive to do this kind of projects. And apart from the company part, I'm also the community manager of the Aero Rust community. This is the Rust community for aerospace applications. I decided to just share the website because you'll find what you need there. We do have a small blog, and also we are planning to release more content, including a newsletter where you'll find, for example, resources shared by some of our members on Discord, and of course the Discord invite, where most of our communication, or this is our place to gather and discuss all topics related to aerospace or Rust. We also do casual meetups every 2 weeks, where we just come together. We usually have some agendas, some topics that someone wants to share about, but it's a casual meetup, so the idea is to just bring the people together and talk about Rust, aerospace, or anything in between. Now, the project I'm going to share with you, it started in 2023 as a workshop, an Aero Rust workshop at Space Conference Plovdiv. I'm very grateful again to Espressif that they provided some parts of the whole kit that we could use as hardware. And you can see on the right people like assembling the frame, but also on the bottom right, the whole assembled workshop kit, and also on the left side you can see all the components that we had. And we really wanted to take this to the next level, so that's why we started working on a workshop with a product like a nano satellite product. But you can find more about this project in part 1 of this talk, which happened on the UA Rust conference in 2024. They should release the video soon, or they have already released them. So definitely check the YouTube channel for that. But you'll find more detailed information about the project itself. And okay, so other than that, what generally what we're speaking about, we wanted to give people this workshop to get started with embedded Rust specifically. So instead of building like actual nano satellites, we decided, okay, let's take this nano satellite, still call it a nano satellite because eventually we want to get to space, but let's give people something tangible, so something that they can build as a whole application and also do experiments with it. So what we have decided so far is to focus on these helium balloons. On the right, you'll see that this is latex balloon. It's usually used for meteorology as well. And you can strap one of these kits and send it to the stratosphere. And of course, there are different sizes of balloons. But at some point, they pop, and you have to go and retrieve your hardware. And on the bottom, that's actually very interesting. NASA launches maybe around 50 of these balloons every year. These are called super pressure balloons, and they can stay up in the stratosphere for months at a time. Apart from the helium part, of course, that's the experimental and how you can develop the project for something useful. We focused on using async or embassy, and it gave us a really nice overview of how you can use asynchronous simply, but also in a full project, basically in a whole project. And of course, the workshop is open source. The current workshop is still in progress, as we're still working on it. There are some exercises for the older version, but now we did some changes. So stay tuned to know more about the latest state. Okay. With that out of the way, what do I want to build, or what was my goal as a setup when I started working on this presentation and this talk? Well, I'm lazy. And frankly, when I was working on this project and constantly moving all the hardware with me, it gets tedious to constantly set it up. I also have cats with my wife, and they can chew on the cables and so on. So it's not really good to carry it all the time with you. And this is sort of the setup I wanted to build. You have this local network. Let's say it could be Wi-Fi. This is the bottom part of the picture. But you can have some kind of a local network, either Wi-Fi, and you can get the hardware with you and plug it in. But what I would like to have is being able to remotely flash a device through the internet. And in this case, we're going to see how you can use VPN. To do that, of course, to have a private network for that. And in this case, I used Raspberry Pi 3, which I had laying around. It's not very powerful, but still for flashing and getting a result, that's enough. And you can see that you not only have the debug probe connected to the hardware, and I'm pointing there because the hardware is there. I'm going to show it in a second. But you do have the debug probe connections. So it could be a single board that you use or multiple ones. And again, your boards can also communicate via USB, for example, or Ethernet. It could be sending packets over USB to communicate with, let's say, another computer. So we have to take this into account when we're not only flashing, but we want to have some kind of a feedback. And this is the general idea I wanted to have. Now, how do we get there? That's the question. Well, we have to talk about the tools. And this is just a simple overview of the tools that you can currently use. First, of course, you have ProbeRS. We do have ESP Flash as well, which you can use on Espressif chips. But ProbeRS also supports Espressif, as far as I know, and it's usually the go-to tool for flashing your devices. Then we have Teleprobe, where we're going to speak about more in details in a bit. And the general notion of this tool was to hack on it, because it's meant for a specific use case, and I'm going to share about that in a bit. I personally use NetBird for the private VPN. And of course, we have this Packet Explorer tool, which I started developing probably 2 years ago, to have a way to explore all the packages that are coming either from the networking or USB, and sort of concise way. But I'm going to share about it in more details in a bit. Okay, so ProbeRS, well, it's easily enough to go to the website and see how you can install it. It's very important to set your UDEF rules, especially in your, on Linux at least. And you're good to go to flash and even debug. Now for teleprobe, and this is the most important part, teleprobe is specifically made for a single use case and for a specific project, and that's the embassy project. It's made so that it can run continuous integration tests with hardware in the loop, basically. And as you can see here, this maintenance status can be found on the README. So we cannot expect this to change for our needs or my needs. So we have to figure out, what's the next step in the ecosystem to provide this tool. And you can find the teleprobe tool in the embassy organization. Now, when I started with teleprobe and I started, doing some of the preparations, I stumbled upon a few issues. First of all, well, it's a very simple and stupid mistake, but it's actually in ProbeRS. The serialization and the serialization of this structure were different. So as you can see here, we have try from. So it will try to create this structure from string, but serializing it actually gives you an object, a JSON object. So this meant that when I tried to list the probes remotely, it was giving me an error, a vague error that I had to figure out and debug and fix. This is easily fixed, right? That's not a big issue. The other problem was that for some reason, when the verification for the flashing on ProbeRS is enabled, probably it's related to teleprobe, but it starts failing. So for the time being, I just disabled it. And that's probably one of the reasons why the workshop onboard computer firmware isn't working. It's a bigger application than just a simple example from Embassy. So there might be something going on there. So I haven't dig deeper into that to actually fix it, which probably should happen at some point. And the last problem I wanted to share is that, well, it doesn't work on Espressif chips, at least for now. There was an open PR, but it got closed. As you saw, the maintenance status of the project was specifically to handle the embassy project needs. So the maintainer decided that this is out of scope, and it's perfectly fine. I think most people have to decide what they want to work on. Otherwise, you get spread out and you don't finish anything. Okay, so we do have teleprobe working, sort of. Then we need the private network. And this is where NetBird comes into play. Underneath, it's using WireGuard, but it gives you a few features on top of it. It's open source, and also if you want to self-host it, you don't need to use their platform. You can self-host it and still get these features that you want. I think for small projects, at least for my needs and the things that I currently do, it's enough. At some point, it might not be enough, but for the time being, it's enough. So if you want to build a VPN and actually work this way, yeah, definitely check it out. And the last but not least, I want to share about this tool I've been working on. At least my understanding, when you start working on a project and you get some data, you want to debug it, or you just want to log the data somehow out of the embedded platform, you want to build some kind of a CLI. And this Packet Explorer is meant to be a crate that you can use to build your CLI for your embedded project and make it easy. Because oftentimes, of course, when we're talking about network listeners, you have UDP currently implemented, but you have other other layers, you have other protocols as well, and these are things that I want to add. But what it's important to know is that every project is different, so, and even every medium is different. So if your embedded project sends one kind of a data type or serialized data over UDP, let's say JSON, it might not send JSON when you're talking about serial communication over USB. So you have to be flexible in how you define these, the serialization and serialization, so that when you receive the data, for example, on your laptop or on the CI or whatever, you can actually perform the deserialization and also do something with the data, or just record it, log it to some data and so on. So this is very important. And I mentioned USB, of course, there's serial, and also I want to add USB to it. So the USB protocol, the ACM, the CDC ACM. Also, I mentioned data logging. I haven't decided how, but for now, just files are enough. And again, many features. Most importantly, again, to bridge the gap between, let's say, the current communities, especially the Arduino ones, and what we have in the Rust ecosystem, we have to of course provide tools for plotting as well. And one of the most known tool in the Arduino community actually comes from the Arduino IDE, where you have this Arduino serial plotter. And apart from the plotting part, I decided to work on the so-called forwarders, which can take the data we are receiving on a specific channel and then forward it to the Arduino serial plotter. This is nice because it bridges the gap if someone wants to come from the Arduino world and C and writing C and join the Rust community and figure out how to do embedded there. Having a tool which is not only useful but also familiar is very important, and I think more people will enjoy coming to Rust if they have these tools. Okay, so with that out of the way, it's time to show you the demo. Now, initially, I wanted to flash the onboard computer with the firmware that we have for it. Again, stripped down version because we don't need all the sensors and so on. But sadly, teleprobe didn't work. So we have to use just the Embassy ADC example in this case. Okay, so first let me just show you what I have here. This is the hardware. You see this is the prototype that we're working on. This is the Raspberry Pi, and the debug probe is connected to it, but also I'm powering the Pico here, the Raspberry Pi Pico in this case. Okay, so what we're going to see again, just for completeness, we're going to see the part where the laptop called Kracho here sends the firmware over the internet through the VPN, through the virtual private network, to the Raspberry Pi, and the Raspberry Pi actually flashes the hardware. Now, I'm going to say out of the bat right now that it's going to give an error, and that's specifically because, as I said, teleprobe is made to run for continuous integration stuff. So it expects the test to run and exit at some point, otherwise it will time out. So in this case, we're running a continuous infinite loop, basically. So after the timeout runs out, then we get an error. But you can still continue flashing the device if you want to. Again, this is only the part with the debug probe. We still don't have the Ethernet and USB part working, but that's for the next time. Okay, so very simply, I do have the Raspberry Pi here opened, and I have the CLI actually built for the Raspberry Pi. And we just call serve. There is a configuration file on the Raspberry Pi which defines a token. You can define other ways to authenticate as well, but also it defines all the debug probes that you have connected, or can be connected to your device. Now that we have the server running, I have prepared the setup, the teleprobe command that will actually flash the ADC example of Embassy. And what you can notice here is that here we do have some Rust log improvements just to clear out some of the stuff that we don't need. But what's mostly important is this cargo teleprobe client. And in this case, we just use this token. We don't use any fancy authentication method. And we define this host, which is in the private network. And of course, we say run, and we say which target. This is the debug probe we have defined in the configuration. And last but not least, the L file, in this case, the release build. And if we run it, we see that it's flashing. We're not going to see logs, again, because of this, that Embassy requires the response and not continuously running the test. And as you can see here, we got around 8 seconds of logs until the deadline was exceeded. This is again in the configuration file, but you can tweak it if for your needs, if you need it. And you can see the logs from the device itself. In this case, the ADC values are from the 3 pins, but also the temperature, the internal temperature sensor. And if we go back to the client side, eventually after the request has finished, you can see still the log from the server, but also the log from the device. So we still get, in this case from DFMT, we still get the DFMT logs. And that's really nice if you want to debug it remotely. This was a simple example and demo that I wanted to showcase, at least how far I got working on it. But when we're talking about, again, these new tools or these limited tools, we have to, of course, talk about what can be done more. And teleprobe and this experiment that I did, with the demo and working on the tool itself, it was a fun little experiment. But as I said, it's only for a single use case and handles a specific project. It won't accept any features that are out of scope. And we're still missing quite a few tools that can be added. For example, staging. I know a company working in the nanosatellite business, or actually already satellites business, that before sending the commands to the actual satellite, they have a duplicate hardware on the ground staying in a rack, which can execute all the commands that they send and also validate that the hardware and the firmware will do what they actually expect it to do. Of course, that means that you somehow need to inject simulated sensory data. And last but not least, as we saw, you have to have some kind of a monitoring system that it does what it does, or it reacts as it should react, or that every data point that you get from the monitoring is okay. And if somebody is interested to discuss this Packet Explorer tool, which is specifically for the monitoring part, I'm open either in this conference or after the conference. You can just come and talk to me. I'm very open, and I try to find some use cases to implement to make it a better tool. And with that, I would like to thank you about your time, and hopefully you have some questions about me. And last but not least, you can find the slides on this URL or the QR code. Thank you.
And we are back for another Q&A. And I'd like to remind our audience to ask questions in the chat. Don't miss the opportunity to talk to our speakers. And to join for this Q&A, I'd like to invite Lachazar. And how are you today? I'm great. Just freed my day so I can watch the conference, and it's been fantastic so far. Yeah, I hope you are enjoying. Have you watched it last day, or this is
Sadly not, because I have a small kid and it's taking a lot of the time. But I did manage to catch some of the talks today, of course, and I'll have some time later to see my friend Omar, actually.
Oh, I see. Yeah, I have 2 kids, so just imagine how tough it is. Yeah. All right. So first, thank you so much for your talk. It's quite inspiring. And before we join live, you showed me some hardware, and I think it would be really nice to share as well with our audience, because I really love it.
Yeah, definitely, I can show it. So as I said on my talk, we're building this educational platform. And of course, this is the very first prototype that hopefully will fly. Hopefully it will not. It's 50-50. So. But the general idea for me, it has always been to get hardware accessible for people and to get started with aerospace. And a person that, as I'm myself, I'm trying to get started from a young age, but I just didn't have the opportunity or the right environment. And I want to create this environment for people, the hobby people, the professionals that want to get into Rust or hardware development, that kind of a thing. And apart from this, I'm also working, on the second version. This is just some of the hardware that it's probably not going to be in the second kit, but just a placeholder for now to run some experiments. Of course, single board computer, some AI accelerator chips, and power, especially to power the two the MCUs here in the lower system, but also the models in the Raspberry Pi. And of course, since I'm working on hardware product, so I have this just mock-up of how the box will, or what the box will contain, just to have something visual to present to people and, show that, hey, someday you'll be able to buy this and, tinker with it.
And how it works, the hardware development for you? Like, do you develop everything by yourself, or there is a community or some other people that help you to develop?
Yeah, so there's a lot of people that actually joined in and are helping in various ways. As I said in my talk, working on aerospace projects usually takes a lot of people, just because it's a lot of things that you need to know, right? From mechanical standpoint or hardware standpoint. I'm a software engineer. I like software, but I really want to get into hardware as well. So that's why I started like a year and a half with hardware as well. And my dream has always been to work in robotics. And this is a way to express myself, right, in the robotics field.
And how can you, or is there anything you can say to our audience, especially for the future engineers, to inspire them into the aerospace or even Rust? Is there anything you can say for them?
Yeah, maybe I can give my perspective on it. I usually don't have a strict plan or steps that I need to take to get to a given goal. It's more that I focus on like a goal further in the road, just planting that in my head and taking one step at a time. Maybe you take the wrong step sometimes, but you still keep going towards that step by step. And I like that idea to, this mindset to achieve anything. Learning Rust, going into aerospace engineering or anything else, just, get started, keep that goal in mind, and head first.
Yeah, and keep moving forward. Even if you failed, try again. That's what usually I say.
Well, people also need to walk backwards, so taking steps back is not bad.
All right. Okay, so again, I like to thank you so much for the talk. I see no related questions right now in the chat, but still we'll get some, and if you can later answer during the conference. And as well, I think you already shared your contact information, so people can get in touch with you if they have any question.
Yeah. Thank you very much for having me. And yeah, I hope to do this again next year.
I'm looking forward to it. All right. And now we can go back to the studio.
Thank you, Pedro. Thank you, Cesar, for that stellar deep dive into hardware in the loop. Folks, we are about to shift gears and talk about one of the most sought-after features of the most Espressif chips. Yes, you guessed it right, Wi-Fi.
Absolutely, and who better to guide us through it than Darian Leung. Darian is very well known in the Espressif community, and he will cover the basics of the Wi-Fi protocol. He will show us how to make the most of it by using ESP-IDF or Arduino.
So, whatever connected IoT device that you are building, Wi-Fi is the key, and Darian is here to help you master it. Let's get connected.
Hi, my name is Darian, and I'm here to talk about Wi-Fi. So this talk is titled Wi-Fi Crash Course, a noob's guide to key terms and concepts. The goal here is to give a beginner's friendly overview of the Wi-Fi protocol. I'll try to cover as many key concepts as I can in 30 minutes, and hopefully this will serve as a crash course in the Wi-Fi protocol. Just a heads up, there's a lot to cover, so this presentation goes fast. But this is being recorded, so you can always rewind and rewatch. So, what's my background? I was a senior embedded software engineer at Espressif. I worked on the software platforms team for over 7 years, mainly working on the ESP-IDF SDK. Now, as a disclaimer, I'm not an expert in Wi-Fi, but I figured what better way to do a noob's guide on Wi-Fi than have another noob teach it. So, what am I going to be covering? Firstly, I'll start off with what exactly the terms Wi-Fi and 802.11 mean. Then, the differences between the wired and wireless mediums. Next, some basic Wi-Fi topologies such as BSS and ESS. Then an overview of what MAC frames are, followed by management operations such as authentication and association. Next, we'll take a look at medium access methods, primarily the distributed coordination function. And finally, some physical layer concepts such as channels. And we'll round off with some further topics and resources. Without further ado, let's begin. So, what exactly is Wi-Fi? In short, Wi-Fi is a technology for wireless local area networks. Well, what is a local area network? In the world of computer networking, networks are classified by spatial scope. So at one end, we have nano networks, and these are on the scale of nanometers. At the other end, we have wide area networks, so these span countries and continents. Local area networks, on the other hand, otherwise known as LANs, are typically at the scale of hundreds of meters. So think residences, offices, schools, etc. The most common technology for wired LANs is Ethernet, and for wireless LANs, otherwise known as WLANs, the most common technology is Wi-Fi. So the terms Wi-Fi and IEEE 802.11 are typically interchangeable. You would likely hear the term Wi-Fi more because it's not a mouthful to say. However, these two terms technically mean different things. To be specific, the term IEEE 802.11 actually refers to a set of protocol standards for implementing WLANs. These set of protocol standards are created and maintained by the Institute of Electrical and Electronics Engineers, otherwise known as IEEE. Wi-Fi is a trademark owned by the Wi-Fi Alliance. Any 802.11 device that wants to be called a Wi-Fi device must be certified by the Wi-Fi Alliance. This certification basically ensures interoperability between different vendors. However, these two terms are typically interchangeable because most consumer devices that support 802.11 are also Wi-Fi certified. The 802.11 protocol has been updated over time to support higher speeds and new features. However, if you try to search for a list of 802.11 versions, you'll be met with a bunch of confusing suffixes. To understand these suffixes, you'll need to know the difference between the main protocol standard and protocol amendments. The main protocol standard is the official document describing how a WLAN should be implemented, and each version of this document is labeled 802.11 followed by the year of the standard's publication. So, for example, here's 802.11 1999, then 802.11 2007, and 802.11 2012. However, those improvements to the protocol standard come from amendments. An amendment is a proposal describing a particular improvement to the Wi-Fi protocol. When a proposal gets adopted, it gets published as an amendment document. Amendments are labeled 802.11 followed by 1 or 2 letters. So here, for example, we have 802.11a, 802.11b, and basically all of these are amendments. Once an amendment gets adopted, it will eventually get incorporated into a future version of the main protocol standard. So here, for example, 802.11n added multiple input, multiple output support. It was adopted in 2009, but this wasn't incorporated until the 2012 version of the main protocol standard. So here's a table showing particular amendments, the year of adoption, and the protocol version that they were eventually incorporated into. However, these suffixes don't make it easy to track what changes were made. Thus, the Wi-Fi Alliance has come up with a simplified generational numbering scheme. Each generation is tied to a particular amendment, and as you can see, the Wi-Fi throughput has only increased over the past couple of decades. Now that we know what Wi-Fi is, let's briefly look at the differences between wired and wireless LANs, and what are some of the benefits of going wireless. Given that we're talking about LANs, let's use Ethernet and Wi-Fi as examples. Firstly, the wired medium can be a unicast. This means when a node transmits a signal down the cable, only the node connected to the other end of the cable receives the signal. Secondly, signal delivery in wired mediums is reliable, meaning if a signal gets sent down the cable, we're relatively certain that it gets received correctly at the other end. In the case of Ethernet, reliability is achieved by using differential signaling with twisted wire pairs. So here, the green pair is one signal, the blue pair is another signal, and so on. Thirdly, wired mediums can be full duplex, meaning that data can be transmitted and received simultaneously. So in an Ethernet cable, the green pair handles the transmit signal, and the orange pair handles the receive signal. However, in the wireless medium, things get much more difficult. Firstly, wireless is inherently a broadcast medium, meaning whenever a node sends a radio signal, any other node within range can receive it. Secondly, wireless is a half-duplex medium, meaning that at a particular frequency, only one node can transmit at a time. This is because simultaneous transmissions from another node will cause interference. And thirdly, wireless is an unreliable medium, meaning if we transmit a radio signal, we can't be sure that it gets received correctly on the other end. This could be due to signal attenuation or interference. But regardless of the wireless medium's complexities, Wi-Fi has still become ubiquitous in most home and office LANs, so there must be some major advantages in going wireless. Firstly, WLANs provide great device mobility, meaning you can move your device around and still remain connected. It's also easier to deploy as you don't need to lay any physical cables, and because it's wireless, it has greater flexibility. Adding or relocating new devices to the network doesn't require any cables to be rerouted. And finally, the ease of deployment and flexibility typically means lower cost to deploy and maintain. However, WLANs also suffer from some drawbacks. Firstly, because the wireless medium is half-duplex, the throughput is typically lower than a wired medium. Secondly, it's less reliable due to interference and signal attenuation. Lastly, it lacks physical security, as anyone with an antenna nearby can receive those radio signals. But Wi-Fi mitigates some of these drawbacks, and the complexity of Wi-Fi mostly comes from this mitigation. Now, let's dive into the implementation details of Wi-Fi. And to start off, let's take a look at network topology. Firstly, let's clear up some basic terminology. The first term to cover is stations. In Wi-Fi, any device that implements the 802.11 protocol is known as a station, or STA for short. More specifically, the part of the device that is considered the station is the Wireless Network Interface Controller, or WNIC. Each station has a unique MAC address, and the WNIC will typically have an antenna and radio for wireless connectivity. The next term is service sets. Whenever multiple stations are grouped together to form a logical network, this is known as a service set. Each service set has an identifier, otherwise known as the SSID, and the SSID is typically a natural language label. Basically, SSIDs are the network names that you see when scanning for nearby Wi-Fi networks. So, for example, these three stations are grouped together as a service set, so they have their own SSID. Likewise with this service set and their own SSID. So, if a service set is a grouping of stations, what are some of the different ways we can group them? This is when we get into topologies. The first topology to look at is the Infrastructure Basic Service Set, otherwise known as a BSS. This is the topology that you most likely use on a daily basis, and it's found in most small office and home office networks. The BSS is made up of a single access point, otherwise known as an AP, and one or more stations. The AP itself is a station, but it also has added capabilities similar to a network switch. This means all stations only communicate directly with the AP. The AP is responsible for forwarding all communications to the correct destination. So here we have a BSS, and that BSS contains an AP and stations K and L. If station K wants to communicate with station L, then K must send the data to the AP, and the AP is responsible for forwarding that data to station L. Each BSS has a unique identifier, known as the BSS ID. This is typically just the MAC address of the AP. An important thing to note here is that the BSS ID is not the same as an SSID. Those are two different identifiers. If a station wants to join a BSS, they must associate with the AP. And stations that are already part of a BSS are known as associated stations. So here, stations K and stations L are associated stations, and if station J here wants to join the BSS, it must associate with the AP. And the last BSS concept to cover is the basic service area, otherwise known as the BSA. This is basically the coverage area of the AP. All stations must remain within the BSA to stay connected, but they are free to move inside the BSA. The borders of a BSA are determined by a signal strength threshold. However, this means that the BSA is fluid, as many factors can dynamically influence signal strength. So, what does a BSS look like in practice? In this example, we have two adjacent apartments, each with their own Wi-Fi networks. So, because they're each their own networks, they have their own SSIDs, and each network contains a BSS. You'll notice some overlap between BSA1 and BSA2. This is why you can see your neighbor's Wi-Fi networks. And with AP1, it's connected to a network switch so that wired and wireless devices can form a single LAN. And there's also a router to handle internet connections. Basically, if you buy an all-in-one router, it'll typically include an AP, switch, router, and even a modem. In summary, the BSS topology is centered around an AP. But because the BSA depends on the AP's coverage, a BSS is limited in coverage area. I'm sure you can think of instances in your home where particular areas have poor Wi-Fi coverage. To address this problem, Wi-Fi also supports grouping together multiple BSSs into something called an extended service set, otherwise known as an ESS. If you've ever used a roaming Wi-Fi network, chances are it's an ESS. So, the definition of an ESS is two or more BSSs connected by a distribution system, otherwise known as the DS. The main benefits of an ESS is that stations can roam over a large service area and still remain connected. To achieve this, there are overlapping basic service areas, and together they form an extended service area, otherwise known as an ESA. And as the station roams around, they'll reassociate with the AP that has the strongest signal. The distribution system is basically a system that interconnects the APs of each BSS, and it can be wired or wireless. The implementation of the DS isn't specified by the Wi-Fi protocol, but the DS must offer particular services. These services include tracking which stations are associated with which AP and forwarding data between APs. Because the ESS is a single service set, all of the BSSs are under the same SSID, meaning they belong to the same logical network. However, each BSS still has their own BSS ID, and from a user's perspective, they will remain connected to the same Wi-Fi network while roaming, and never even notice that they've switched APs. Let's look at an ESS in practice. Let's say we have a Wi-Fi network for an office, and this network contains 3 BSSs with overlapping BSAs. So here's BSA1, here's BSA2, and here's BSA3. Now, because they're all part of the same network, they all share the same SSID. As station A enters BSA1, it can now join the network by associating with AP1. And if station A here wants to communicate with station B, the data flow is as follows. Station A will send the data to AP1, AP1 will then forward that data to AP2 over the distribution system, and then AP2 will then finally forward that data to station B. So as station A roams around, it will enter and exit different BSAs. So here, it's exiting BSA1 and entering BSA2. So at some point, AP2's signal will become stronger, and station A will end up reassociating with AP2. And as station A continues to traverse the extended service area, it will keep reassociating with APs that have the stronger signal. And because there are overlapping BSAs, we can ensure that there's seamless connectivity. Now that we've covered basic topology, let's look at what data is actually sent by each station. These are known as MAC frames. Frames are a basic unit of transmission, meaning whenever a station or AP transmits something, that transmission is a series of bits that adhere to a well-defined format. Frames consist of 3 parts, which are the header, the body, and the frame check sequence, otherwise known as the FCS. The frame body contains the payload of the transmission. The frame body is optional, as there are instances where the transmission contains no payload. The FCS is the checksum calculated based on the bits inside the header and the body. And the frame header contains metadata about the frame itself. For example, it has multiple MAC address fields to indicate the source, receiver, and destination of the frame. There's also a sequence control field to help with segmenting larger payloads over multiple frames, and there's a frame control field which indicates the type of frame. We'll get into the meaning of what these fields mean in the later slide. In Wi-Fi, frames are categorized as data frames, control frames, or management frames. Data frames carry data from higher layer protocols, so something like IP packets. The higher layer data is encapsulated in the body of the data frame. Control frames assist with the delivery of data frames, thus have no body and are typically found as part of multi-frame exchanges. For example, in this diagram here, this shows a typical multi-frame exchange required to deliver a data frame. Here, the RTOS, CTS, and ACK frames are all control frames. The RTOS and CTS frames are used to clear the channel, and the ACK frame is used to acknowledge that the data frame was delivered successfully. Management frames are used to manage the wireless network and includes frames for management operations such as scanning, association, reassociation, etc. Recall that the wireless medium is a broadcast medium, so a frame transmitted by a station can be received by all other stations within range. Therefore, each frame needs some metadata to indicate which stations the frame was intended for. In a Wi-Fi frame, this is done through a combination of the MAC address fields and the to and from DS bits. The to DS bit and the from DS bit are part of the frame control field of the header, and they indicate the directionality of a frame. If the to DS bit is set, it means that the data frame is headed towards a distribution system. So this could be a data frame from a station to an AP. Likewise, if the from DS bit was set, it means that the frame was coming from the distribution system. So this could be a data frame from an AP to a station. So the 2-bit combination of the two DS bits and from DS bits determine how the address fields should be interpreted in the frame header. As mentioned previously, each Wi-Fi frame header contains multiple MAC address fields. Each MAC address is 6 bytes long and shares the same address space with Ethernet. There are 4 types of MAC addresses that can appear in a Wi-Fi frame header. The source address is the address of the station or Ethernet node that was the original source of the MAC frame. The destination address is the address of the station or Ethernet node that is the final destination of the MAC frame. The transmit address is the address of the station that transmitted the Wi-Fi frame, and the receiver is the address of the station that should process the Wi-Fi frame. So let's take a look at an example here where station X wants to send a MAC frame to the PC. What will happen is that station X will send a Wi-Fi frame to the AP. The AP will then convert that to an Ethernet frame and forward it to the PC. So within the Wi-Fi frame, it's heading towards the distribution system and not from the distribution system. So we'll need to look at the green row for what the addresses should be. So the source address is station X and the destination address is the PC. But the transmitter address is station X and the receiver address is AP1. The rest of this table shows what each address type means for each direction of Wi-Fi frame. Looking at this table, you see that in most cases, one of the addresses is repeated. Therefore, it's not necessary for a MAC header to always include 4 address types. Because not all address types are required, the address for field is optional. Each address field can represent one of the previously mentioned address types or the BSSID. The interpretation of these address fields is determined by the 2 DS bits and from DS bits. So, looking at the previous example, address 1 will be the receiver address, which is the same as the BSSID. Address 2 will be the transmitter address, which is the same as the source address. Address 3 will be the destination address, and address 4 doesn't exist. So now we move on to management operations. Management operations are the actions taken by stations and APs to establish and maintain a connection. This is a cooperative effort between stations and APs, and this typically involves them exchanging multiple management frames. There are numerous management operations, but the main ones to cover are scanning, authentication, and association. To start off, let's talk about how stations discover the existence of a BSS. This is done through beacon frames. Beacon frames are a type of management frame that allows APs to announce the presence of the BSS. Beacon frames are transmitted periodically by the AP, and the beacon interval is configurable. Inside the payload of beacon frames are numerous data fields carrying information about the BSS. This includes things such as the network's SSID, the capabilities of the BSS, and a timestamp used to synchronize the stations in the BSS. Scanning is a management operation for stations to discover Wi-Fi networks. Scanning can either be passive or active. With passive scanning, this involves stations listening for beacon frames from APs of different BSSs. Different BSSs operate at different frequencies, otherwise known as channels, so a passive scan will sweep through multiple channels. Active scanning involves a station sending a probe request frame. If an AP receives a probe request frame, it will respond with a probe response frame. Similarly, active scans will also sweep across multiple channels. The result of scanning is a generation of a scan report. This is basically a list of all discovered BSSs and their capabilities. Furthermore, when scanning, stations can apply a scan filter to filter out BSSs based on certain parameters such as SSID, service set type, etc. Once a station has found a suitable BSS to join, the station must be authenticated before it can join the BSS. The most basic authentication procedure is known as open system authentication. Basically, it's just a simple handshake between the station and the AP. Note that this authentication provides no meaningful security, and it simply ensures that the station and the AP have compatible capabilities. The authentication procedure involves the station sending an authentication request frame, which is then acknowledged by the AP. The AP then sends an authentication response frame, which is then acknowledged by the station. Lastly, the association procedure allows a station to join a BSS. The procedure involves a station sending an association request frame, which is then acknowledged by the AP. The AP then responds with an association response frame, which is then acknowledged by the station. For each station that associates with the AP will assign them a unique association ID, otherwise known as an AID. This AID is then included as part of the association response. The AP must also inform the distribution system about station associations. This is so that the distribution system can keep track of which stations are associated with which AP in order to correctly forward frames to different BSSs. As a station roams, it will need to reassociate with another BSS. Reassociation is similar, and it involves a reassociation request frame and a reassociation response frame. When the new AP receives a reassociation request, it will contact the old AP over the distribution system to let it know that the station has been reassociated. The new AP will then assign the station a new AID, and the AID is included in the reassociation response. Now we'll move on to the medium access method. In other words, how can multiple stations share the wireless medium? The act of coordinating different nodes is known as medium access control, or MAC. And the MAC technique that Wi-Fi uses is known as the distributed coordination function, otherwise known as DCF. The DCF is distributed, so it doesn't rely on the AP to coordinate transmissions of all stations. Instead, the coordination within the BSS is a cooperative effort between all nodes. Other techniques, such as a point coordination function or hybrid coordination function, are built on top of the DCF. However, I won't be covering those other techniques in this presentation. So, some of the features of DCF include using CEST as the multiple access method, having frame prioritization using an interframe spacing mechanism, and also using virtual carrier sensing to allow stations to save power. I'll get into the details of these features later. Firstly, let's take a look at the shared wireless medium. Recall that if two or more nodes transmit simultaneously on the same channel, interference will occur. However, all nodes within a BSS operate on the same channel. Therefore, communication must be half duplex. Secondly, due to various RF properties such as attenuation, not all stations in the BSS can hear each other. For example, station X here could be transmitting to the AP, but station Z is out of the coverage of X, so station Z will have no idea that station X is transmitting. This is known as the hidden node problem. However, keep in mind that within a BSS, all stations must be within range of the AP. Otherwise, they wouldn't be able to join the BSS in the first place. So, given these properties, there needs to be some way to coordinate multiple stations so that they don't transmit at the same time. Furthermore, we need some way of dealing with the hidden node problem. Carrier sense multiple access with collision avoidance, otherwise known as CEST is a method for nodes to share a wireless medium by avoiding simultaneous transmissions. Carrier sense multiple access basically means that each node wanting to transmit must listen to the medium first and wait until the medium is idle before attempting to transmit. However, if the medium is idle, it's possible for two nodes to attempt transmission simultaneously. This is known as a collision, and we can avoid that by having each node use a random backoff timer. So, for example, here's 3 stations where station 1 is currently transmitting, so the medium is busy. Once station 1 is done transmitting, the medium is now idle. There's an interframe space where all nodes need to wait for before starting their contention window. This is where each node starts their random backoff timer. And let's say station 3 here had the shorter backoff timer, so it starts transmitting first. Station 2 will sense that the medium is no longer idle, and it will know that it needs to wait for the next idle opportunity before it can transmit. The contention window is divided into n slots, where n is a power of 2 minus 1, such as 31, 63, 127, and so on. The random backoff time for each node is determined in terms of slots. So each time a node wants to transmit, they'll pick a random integer r, and the length of their backoff time is r slots. However, CSMACA alone is not sufficient. The hidden node problem could still lead to collisions. To demonstrate this, let's say we have station X and Y in a BSS. Both stations are in range of the AP, but not in range of each other. Let's say the AP is transmitting here, and after it's done, the medium is idle. Then the contention window begins. Station X and Y both want to transmit something, so they start the backoff timers. Let's say station X had the shorter backoff time, so it starts transmitting first. However, because station Y is completely out of range of station X, station Y will think that the medium is idle, so it will start transmitting as well. The result of the simultaneous transmission is that there's a collision for the AP. Furthermore, only the AP detects a collision. Station X and station Y will have no idea that a collision occurred. Therefore, we need some way to confirm the successful delivery of a frame. The solution to the hidden node problem is a four-way frame exchange. This exchange involves a request to send, clear to send, data, and acknowledgement frames. The RTOS and CTS frames are used to clear the channel before transmitting a data frame. Using the same example above, if station X transmits an RTOS frame, then the AP will send a CTS frame back to indicate that the channel is now clear. However, if there was a collision at the AP, it will not respond with a CTS frame. This indicates to station X that it needs to retry at some later point. Likewise with the acknowledgement frame, if station X sends a data frame to the AP and there were no collisions, the AP will respond with the ACK frame. The lack of an ACK frame indicates to station X that a collision occurred and it needs to retry. Note that the four-way exchange only deals with collisions, but it does not prevent collisions. Something else to consider is how do we make multi-frame exchanges atomic? In other words, how do we make sure that another station does not send an unrelated frame during a multi-frame exchange? For example, here we have a four-way frame exchange where the AP is sending a data frame to station X. What we expect to happen is that station X should respond with an ACK frame. However, when the medium becomes idle, what if an unrelated station Y has a shorter backoff time and ends up sending an unrelated frame? So this could mean that the four-way frame exchange gets interjected by some random frame. Essentially, there needs to be a way of ensuring that the multi-frame exchanges are atomic. And this is achieved by using different interframe spaces. So if you recall, the interframe space is a period of time following the end of a frame. By having shorter interframe spaces for certain frames, we can guarantee that those frames will have priority. Wi-Fi has multiple lengths of interframe spaces, but the ones we're going to discuss today are the short interframe space, otherwise known as CIFS, and the DCF interframe space, otherwise known as DIFs. CIFS is the shortest interframe space, thus is for the highest priority frames such as CTS and ACK frames. This makes sure that the frame exchanges are atomic. DIS is a longer interframe space, followed by a contention window to allow for stations to contest for the wireless median. DIFs is typically used for the first frame of most multi-frame exchanges. The last medium access concept we have to cover is carrier sensing, which is the method used to determine whether the medium is busy or idle. Firstly, we have physical carrier sensing, which is when a station keeps its radio powered and is actively listening to the medium. However, keeping the radio powered is power intensive, and the hidden node problem could also lead to false idle conditions. Therefore, Wi-Fi also has virtual carrier sensing, which is the method of tracking whether the medium is busy without the need to physically sense the medium. The way this is achieved is through the network allocation vector, or NAV. The NAV is basically a timer in each station, which indicates how much time is left until the medium is idle. This allows the station to shut down its radio to save power and power it back on only when the NAV expires. So, how does the NAV know how long the medium will be busy for? Recall that there was a duration ID field in all frame headers. This field basically indicates how long the medium is going to be busy for. So let's take a look at an example. Here we have a typical four-way frame exchange between the station and the AP. As the station sends an RTOS frame, the RTOS frame's duration ID field will indicate how long the medium will be busy for the entire four-way frame exchange. And just in case there was a hidden node, all stations are within range of the AP. So when the AP sends a CTS frame, the CTS's duration field will indicate how long there's left for the four-way frame exchange. So the result of this is that all nodes within the BSS will have their NAVs updated as a result of the RTOS and CTS frames. So they can go ahead and shut down their radios and wait until the NAV expires here before they power it back on and sense whether the medium is physically idle or not. Now we get to the physical layer. The physical layer is quite complex, so I won't be able to cover it in detail. So if you didn't already know, wireless communications use radio waves. And in the electromagnetic spectrum, radio waves occupy the lower frequency end of the spectrum. The radio spectrum is split into bands, and the usage of most bands is strictly regulated and requires a license. However, there are certain bands which are not licensed. These are known as the industrial, scientific, and medical bands, otherwise known as the ISM bands. The ISM bands that Wi-Fi uses is a 2.4 GHz band, which actually ranges from 2.4 GHz to 2.4835 GHz. And there's also the 5 GHz band, which ranges from 5.725 GHz to 5.875 GHz. And within the ISM band, Wi-Fi divides up the band into multiple overlapping channels. The number of channels differs depending on region and country. However, all stations within the BSS must operate on the same channel. So the point of multiple channels is to allow for channel selection. Network designers can pick channels to avoid interference from the environment and also neighboring BSSs. Typically, what will happen is that each BSS will use a non-overlapping channel from a neighboring BSS. For example, channels 1, 6, and 11 are non-overlapping. So when selecting channels for a BSS in an extended service set, we need to make sure that each BSS uses a different channel that doesn't overlap with the neighboring BSS. So that's all the content we have time for in this presentation. However, Wi-Fi is still a complex protocol and there's a lot more to learn. As a follow-up, here's some further topics I recommend you take a look at. Firstly, there's some topologies that we didn't cover, such as the IBSS and MBSS. For MAC frames, there's also the idea of fragmenting. And for security, I suggest you take a look at the WEP and WPA protocols. For power saving, there are two methods you can take a look at, which are the PS pole and target wait time. As for modulation schemes, this could be entirely its own topic, but you can take a look at some modulation schemes used in the Wi-Fi protocol, such as DSS, OFDM, OFDMA, and QAM. And finally, if you're interested in getting a copy of the slides, you can find them on my GitHub. And in terms of beginner-friendly books, I suggest the Definitive Guide by Matthew Gass and the CWNA Guide by Coleman and Westcott. Large parts of this presentations were based on the contents of those books. So, thanks for watching, and I hope you learned something today.
Thank you, Darian, for that comprehensive breakdown of the Wi-Fi protocol. Sergey, speaking of Wi-Fi, I'm sure you must be knowing about one of the most common, most popular Wi-Fi based protocols, communication protocols from Espressif, the ESP-NOW.
Of course, Sudeep. And I love ESP-NOW. It's one of the best ways to establish a wireless connection between multiple ESP devices.
That's right. And to tell us more about its performance in indoor environments, we have Michal Kubaszczyk from the University of Žilina in Slovakia. Michal has been evaluating how different placements within a building impact the reliability and success rate of ESP-NOW packet transmissions.
If you are working on projects with ESP-NOW, this talk will be useful for you. Let's welcome Michal Kubaszczyk.
So, hello, my name is Michael, and our presentation is about the implementation of ESP-NOW protocol in indoor applications. So we will go through some content about smart indoor applications, then some comparison about or comparison of ESP-NOW and Wi-Fi. We will go through some concept of network that we designed and results, and at the end we will have some conclusion and recommendations for you to implementation of ESP-NOW protocol. Our team is from Department of Technical Cybernetics from the Faculty of Management Science and Informatics, University of Žilina. Our department ensures a field of study computer engineering, and most of the applications of students or research projects are based on ESP32 modules or development boards. So let's talk about some smart indoor applications, some real-life applications. Smart applications brings up interconnection of multiple sensors via wired or wireless connection. Basic concept of smart application consists of some measurement unit, some processing unit, and some actuator unit. So measurement unit consists of some microcontroller or microprocessor with connected sensors. Then we have the processing unit, which is mostly some high-performance microcontroller or single-board computer, maybe some cloud system. And then we have actuator unit, which can be probably heating, cooling, watering, or lighting. So on the left picture, we can see some device concept or some node of a smart application that have some sensors. It can have some user input for configuration, and then it can have some output for actuator unit probably, and it communicates with some central point or some cloud. On the left, on the right picture, we have design of network with multiple devices that are connected to the central point, and the central point is communicating with cloud. So some examples about or some examples of smart indoor applications. It can be smart lighting, smart plugs. It can be air quality monitoring with air recovery, or some soil moisture monitoring with water control. Then it can be some machine status monitoring, inventory management, player tracking, for example, tracking players in a laser game or escape room, or some search or rescue systems. We can use some wired or wireless communication. Wired communication is mostly used between microcontrollers or microprocessors and sensors. It can be UART, I2C, or SPI. And then we have wireless communication that is used between sensor nodes or nodes and processing unit, maybe cloud, and mostly is used Wi-Fi, Zigbee, Bluetooth or Bluetooth Low Energy for low power applications, then Matter, Thread, and ESP-NOW. About some most used wireless protocols, Wi-Fi, it has 2.4 gigahertz and 5 gigahertz frequency bands. Range is up to 30 meters. Then we have Zigbee that is uses industrial, scientific, and medical radio bands, including also 2.4 gigahertz or 915 megahertz in America and 868 megahertz in Europe. It has range of 10 or 20 meters indoors, but it can be extended through the mesh networking. Then we have Bluetooth or Bluetooth Low Energy, which is also 2.4 gigahertz band and a range of 10 or up to 100 meters. And the last is ESP-NOW, which is also 2.4 gigahertz band, and the range is around 200 meters. So let's talk about some comparison of ESP-NOW and Wi-Fi. Wi-Fi provides connection of the device to the internet over wireless connection. It's universal, implementable for any device, supporting 2.4 gigahertz frequency or 5 gigahertz. It supports many protocols such as UDP, TCP, HTTP or HTTPS, FTP, and it supports all variants of network architecture like mesh, peer-to-peer, star. About ESP-NOW, it's implemented on ESP8266 and ESP32 based modules. It provides only peer-to-peer communication, up to 20 peers per device. And also buffer is limited to 250 bytes. So let's compare them. Wi-Fi can provide communication with various type of systems. So if you are using Wi-Fi, you can communicate with every device that supports Wi-Fi. Any developers or development modules for any company. When you are using ESP-NOW, you can communicate with systems based only on ESP modules. Wi-Fi has also high latency. ESP-NOW has low latency. Wi-Fi has uplink like 554 megabits per second, and ESP-NOW is up to 250 kilobits. About the range, Wi-Fi is up to 30 meters and ESP-NOW is up to 200 meters indoor. Wi-Fi has higher power consumption with for ESP32 modules. During the connection to the Wi-Fi, it can have a peak of 1.5 amperes, and the ESP-NOW has lower lower power consumption. It has during the sending it has 100 milliamps. Wi-Fi is also mainly for internet connection, so sending to some cloud, some REST API, some server, and ESP-NOW is designed for IoT, some low power application. So let's talk about the concept of our data evaluation. So what was the motivation of this project? We wanted to evaluate range and packet loss or latency of the ESP-NOW protocol for indoor applications. So according to placement in the building, and also according to change of environment. It has a use case in a smart classroom project of our students. So the concept of the network, we have like 8 nodes, sensor nodes, communicating via ESP-NOW with a central unit, and the central unit harvest data and send it through the Wi-Fi to the ThinkSpeak. So sensor nodes has been ESP32 based device that simulates sensor data, and the central node is ESP32 S3 and ESP32C6 combination. These two modules communicate via UART. So sensor nodes sends data to the ESP32S3, and it sends via UART to C6 and send it to ThinkSpeak. Sensor node is also implemented in MicroPython, so we wanted to evaluate that is not depend on some implementation or some programming language, and it has also ability to change channel or power of the signal by request of a central unit. Then we have central node. Both parts, like C6 and S3 part, is implemented in C, C++. ESP32S3 is able to send the request for change of channel of the nodes and also power of the signal of the nodes. And ESP32C6 is just receiving the data from ESP32S3 and send it to ThinkSpeak. So maybe you can ask why we use 2 modules for this central node. It's because that when you are connected to the router via Wi-Fi, and you have implemented also Wi-Fi and also ESP-NOW, they are sharing the antenna. So if you are connected to the router, it uses like 90% of time. So the packet loss increases. So it's like only 10% of time for ESP-NOW. Concept of device placement. On the picture we can see map of the department and also placement of the nodes. So the central unit is in one office and nodes are in the other classrooms on our office. So we can predict that it has another signal quality due to multiple walls and structure between the peers. So we can came to the results. So some evaluation of packet loss and signal strength. So evaluation of packets. Evaluation of the packets has been done by counting the packets in period of time. So we have a stable frequency of sending. Relative reliability or latency is calculated like a ratio of received packets and expected packets. And packet loss is calculated by ratio of non-received packets and to expected number of received packets. Exactly the implementation was that we have been sending packets every 250 milliseconds. So basically 4 packets per second. Expected number of received packets was for 30 seconds. So it was 120 packets with 0% packet loss. In first comparison, I have marked on the image, on the picture, the nodes that have been evaluated. So we have central unit and we can see node 1, node 2, node 3 in the right top corner of the classroom and node 4 in the office. On the graph we can see packet loss during the time. So you can see that node 1 has approximately 0% packet loss. Also node 4 and node 2 is debatable. So it has sometimes it has less packet loss, sometimes it's like 100% packet loss. And also node 3 is almost 100% packet loss. In the second comparison, we have another 4 nodes. So we have node 5, node 6, node 7 in the other corner of the classroom, and node 8. And on the next graph, we can see that only node 6 has approximately 0 packet loss, and the others have almost whole time 100 or really high packet loss. The last comparison is for best latency, and the lowest packet loss has been achieved by nodes 1, 2, 4, 6. So it was the nearest one. On this graph, we can see that only node 1, node 4, and node 6 has approximately 0 packet loss, with 1 peak in node 6. And only node 2 has a packet loss somewhere between or around 50%. So we can came to the conclusion and some recommendations for you. So 50% of nodes are reliable, and packet loss really highly depends on the structure of the building and the number of the walls and structure of the walls. and also percentage of open space between the devices that are communicating together. Some future readings, inspiration for you, and some next research. Research leads to add more nodes and further increase precision of analysis. We will also do some analysis of signal over the multiple floors. So if it is the same as through the wall, we can use directional antenna for higher signal strength, and probably the last part would be analysis or find the best place to place the central unit. So the place would be with the lowest packet loss, and we can then change power of the signal of nodes to reduce power consumption of the nodes, because power consumption of nodes are highly depending on power of the signal. So some recommendations for indoor applications and ESP-NOW. You should divide the building to segments with the highest percentage of open space, and maybe usage of multiple central units. And also central units can communicate by ESP-NOW, but you should use probably directional antenna, and implementation of software control of packet delivery, and then some solving of the issue if there is a non-delivery status. Thanks for watching.
Thank you, Mikhail, for that in-depth look at ESP-NOW and its performance. Sergey, if you remember, on day one of DevCon24, we learned about the status of Zephyr on Espressif devices.
Yes, sure. And today we have a great chance to see it in action. Folks, up next we have Pedro Bertoletti from Eldorado Institute in Brazil, who is going to take us from theory to practice. He will demo a real-world example of Zephyr in use, a GNSS tracker running on ESP32 using LoRaWAN.
So, if you're evaluating Zephyr for your next IoT project, don't miss this talk. And let's welcome Pedro Bertoletti.
Hi, my name is Pedro Bertoletti, and today I'll talk to you about Zephyr RTOS, used as a versatile development for embedded software in ESP32. This presentation is made on behalf of Instituto de Pesquisas Eldorado. Before starting this presentation, I will give some background about me. I'm a Brazilian technology consultant focused on embedded system development and IoT project solutions development. I have more than 15 years of experience in embedded device and IoT solutions development, and also I have worked in several areas like industrial applications, low power communication, consumer electronics device development, and more. Now I'll talk a little about a company I work for, Instituto de Pesquisas Eldorado, or Eldorado for short. Eldorado is one of the greatest research institutes here in Latin America, based in 4 strategic cities here, which are Brasilia, Porto Alegre, Campinas, and Manaus. For 24 years, Eldorado has developed tailored software and hardware solutions for various industries, standing as a major articulator of open innovation with projects that put Brazil on the technology roadmap. Eldorado is a world-class R&D and I provider developing state-of-the-art software and hardware solutions. It's a protagonist of open innovation, is an ERTO member and partner of innovation hubs. Here's the agenda for today. It covers from showing what Zephyr project is to a practical example showing how Zephyr RTOS can be put in action using ESP32 based project. Now, first things first, let's check what Zephyr RTOS project is. Zephyr RTOS is a Linux Foundation-hosted collaboration project created in 2016. It's an open-source collaborative effort, uniting both corporate and independent developers from all over the world, helping build Zephyr RTOS as a small, scalable, real-time operating system. As a result, Zephyr RTOS is now an embedded operating system supported by several microcontrollers and SoCs families, like ESP32, for being applied in a huge variety of embedded system solutions. Here is a cut of how big Zephyr RTOS is today. It counts on more than 2,000 independent contributors. Also, Zephyr RTOS is composed by 140 repositories, summing up more than 45,000 pull requests concluded. Regarding hardware support, Zephyr RTOS is currently supported by more than 100 development boards, and it's also supported by 10 different microcontrollers and SRCs architectures, including ESP32 SoCs and solutions, including the RISC-V architecture. As a direct consequence of high engagement by developers all over the world, the features covered by Zephyr RTOS nowadays are really vast, as seen as this slide. As seen in Linux-based systems, Zephyr RTOS counts on high modularity. It supports advanced and bulletproof threading and memory resources management, including multiprocessor support, which makes Zephyr RTOS a very scalable and stable solutions operating system. Regarding connectivity, it is very, very vast too. It supports Bluetooth Low Energy, or BLE for short. It's 80.15.4 compliant too, and counts on native and fully featured network stack, making Zephyr RTOS a very, very good option for Internet of Things device as an embedded OS. Regarding licensing, Zephyr RTOS has a LTS release, and it's licensed on Apache 2.0 permissive software license. So you can use Zephyr RTOS as both proprietary and commercial solutions. Now, let's take a look on how Zephyr RTOS is organized. Let's check how are the main RTOS subsystems and how Zephyr RTOS is put on. Well, first thing to learn regarding Zephyr organization, it's this block diagram, as you can see on the left side of the screen. This block diagram shows on its upper side or its upper part the most common components of a Zephyr RTOS, that is a collection of third-party libraries, application services, OS services, the kernel itself, and HAL. And on the lower part of this diagram, you can see some specific tools that Zephyr RTOS make use of to enable developers to make applications and make solutions using Zephyr RTOS. From those, I would like to highlight two of them, which is West and Bootloader. West is a Swiss arm knife of Zephyr RTOS. Developers use this West tool for almost everything in Zephyr RTOS, from preparing development environments to compile and debugging, and also flashing the target, which is, in this case, ESP32. And Bootloader, of course, a Bootloader is not a specific tool from Zephyr project, but Bootloader, it's a very special topic here in Zephyr, because Zephyr can use target specific bootloaders or a default bootloader. Zephyr uses MCU boot as default bootloader, but it can use, as I said before, some target specific bootloaders, as happens in ESP32. And also, regarding the build system, Zephyr RTOS uses CMake. Proceeding to the Zephyr RTOS organization topics, I would like to present some important or some very common subsystems here. As you can see in this slide, Zephyr RTOS support many subsystems, and most of it are very look-alike or is the same as you can see in embedded Linux. So you can count on debug subsystem, DFU, which stands for device firmware upgrade subsystems, logging subsystems, shell subsystems, and so on. So there's a huge variety of subsystems Zephyr RTOS can support, and you can check a little more about them on this website. Now it's time to check how a Zephyr RTOS application project is organized, okay? As you can see in this slide, an application project using Zephyr RTOS is composed by some folders and files, which is represented in this figure on the center of the screen. The first of figures I would like to highlight is the board folder, sorry. This board is mandatory and contains all project device tree overlays, which stands for DTO files for any specific target configurations. So it means that each DTO file can describe the hardware used for a specific target. So each microcontroller or each SoC that should run this application should have a separated or a dedicated file, DTO file, in this folder. Now is the SRC folder, which is also mandatory. It contains all application source codes, which means .c, .h, .cpp files, and so on. Regarding getting deeper into the build system of Zephyr RTOS, it uses CMake, as I said before, and the CMake list file, which is also mandatory, can be found here at this structure. And this file is comprised of a set of directives and instructions describing the application's project source files and targets, which means executable, library, or both. The kconfig file is also mandatory, and for those who are used to develop with embedded Linux environment or develop embedded Linux solutions, it works the same. So the kconfig files here specify the application project's specific kernel configurations for this project. Also, another mandatory file, which is prj.conf, and it contains common kernel configurations that should be applied to the application project regardless of the chosen target. So here's a point of attention. Kconfig file is specific for kernel configurations, and here is the kernel configurations that should be applied regardless of the chosen target. So if you have a kernel configuration that should be applied regardless you're using a ESP32, STM32, or any other microcontroller, it should be here. And finally, here's a sample.yml file, which describes the application project features, which means the features of the project to be listed in the Zephyr RTOS contribution, okay? So this file is optional, so it's only required when there is an intention to share or to submit this project application to as a Zephyr RTOS open source official contribution. So if you are not intended to do this, you are not obligated to write a sample.yml file. Now it's time to check how device tree overlays, or DTOs for short, are used in Zephyr RTOS to offer versatility and scalability for embedded software that runs Zephyr RTOS. Well, let's start by defining what is device tree overlays, or DTO for short. DTO stands for a resource that allows developers to describe the hardware peripherals wired to the target. So that kind of peripherals that aren't self-announced, like USB or something like that, need to be described, need to be told. Kernel system, the operating system kernel needs to be told which hardware are wired to what interfaces. So DTO does this job. It contains a description of what is wired where. DTO files tell OS what pieces of hardware it must handle to. As you can see in the right side of the screen, it's an example of a node, a DTO node, that describes a SPE node, which contains a sensor, BME280 by Bosch. So this node describes that there is a sensor that should be handled by BME.80 driver, and this sensor is using SPI interface and also using GPIO 17, and pin control is related to SPO0 default, and so on. So the device tree overlay files describe the hardware wired to the target. Zephyr RTOS use DTO files to describe hardware for each target that solution must support. This is a very, very nice feature of device tree overlays, very, very nice usage of device tree overlays in Zephyr. So this very same application code can be built for multiple targets without changing a single line of application source code. So it means if you have a DTO file for each architecture that your application or your project should support, should run into, you must have a DTO file for each of them, and then only specify for which target you want to buy it or to build it, and it will be built for the specific target that you specify. This is very useful for solutions that must have as minimum production costs as possible, making it possible to rapidly and almost effortlessly port a project to another target and optimize the manufacturing costs and development costs. Well, there's a comparison between the DTO usage in embedded Linux environment and in the Zephyr RTOS development. Despite of DTO files are described and written the same way in both environments, there's a little difference on when it comes to use. I mean, in embedded Linux environment, DTO files are interpreted at boot time in a dynamic way, which means to say that if there's a bug in DTO file or some type error or something like that, it's impossible to find it out when you are compiling Linux or you are compiling embedded Linux application. So you'll find out this bug or this error only after booting the system. But in Zephyr RTOS, DTO files are aren't interpreted at boot time. They are interpreted during the Zephyr RTOS compilation time. So if there are some errors or some typo or something like that, when you are compiling the Zephyr RTOS with these DTO files, it will raise an error or raise a warning depending on what's wrong, and you'll be able to find out what's wrong before booting the system. So it is very good for development, in my opinion, because it saves you time. Well, now let's check which are the main benefits that Zephyr RTOS can offer to enhance the scalability and real-world embedded software solutions. The first benefit I would like to highlight is the improvement of embedded software modularity and low copy level achieved. Like seen in embedded Linux solutions, Zephyr RTOS is composed by a kernel, by some drivers, and a collection of software, which we call application. It works like playing Lego. I mean, everything can be abstracted like a layer or like a block, and you put everything together as your solution requires. So using Zephyr RTOS and enabling or putting some subsystems, some blocks together is like playing Lego, okay? It makes very easy to add, fix, or replace drivers, libraries, and also very easy to change target without harming or getting damage to their product as a whole. So Modularity and low coupling are very, very welcome features, and Zephyr RTOS can provide it. Well, the second benefit I would like to highlight you is the scalability and versatility that Zephyr RTOS can offer. As said before, if you have a DTO file for each architecture or each target your solution must support, you can develop a target agnostic solution, which means the application code is the very same and doesn't depend or doesn't make references to the target, to the deep target features. So you can modularize and how can I say, isolate the hardware specific features from the application. So having target specific files for each microcontroller or SoC, as I said before, using this, it's possible to build the embedded solution for any supported targets you want without changing a single line of application code. It's very, very nice, and it saves you a lot of headache when porting products from another architecture or another SoC. Well, the third benefit of using Zephyr RTOS is it's open source. Zephyr RTOS is a big and very active open source project, as we've seen in the beginning of this presentation. It's a huge project right now. So it means to say it's constantly being improved or constantly being fixed too. And new features from Zephyr RTOS comes out every day. And developers count on a community support, a very active community support, by the way, for asking questions, discussing bug fixes, making questions, and so on. So Zephyr, it's a very, very friendly for developers because it's open source and it's very, very competitive. You can count on people to help you from community if you need. Zephyr RTOS also have a long-term stable, which or LTS for short version. What's perfect for using it in products that should be manufactured or sell for years. So it adds reliability and also quality to the embedded software, as long as you have a long-term stable version available. The next benefit I would like to highlight is that Zephyr uses a permissive open source software license. Zephyr RTOS is licensed under Apache 2.0 software license, which means it's a permissive open software license, allowing both commercial and private use. So as Apache 2.0 isn't a copyleft software license, you have this flexibility or this easiest to make it usable for commercial products. Okay, so if you want to develop something to sell, if you want something to build your own product, you can use Zephyr RTOS without having headaches regarding licensing and sharing some private or some how can I say, some not public code. You won't suffer from that. Therefore, developers and embedded software companies can use Zephyr RTOS in their products. Okay, so it's good to sell, good to use in real world products, and so on. Now let's go on. Now let's see the source code of a full project that use Zephyr RTOS as an embedded operating software. Let's check in this case, a LoRaWAN tracker that uses Zephyr RTOS as an embedded operating system using ESP32 WROOM32 as a microcontroller or as a target. Before going to the code overview itself, let's check some requirements. Before proceeding to try to reproduce this project in your machine, I would like to give you two requirements or 2 points of attention that you should follow. Okay, the first one is you should prepare your RTOS Zephyr RTOS environment by following the Getting Started guide, depending on your operating systems in your host machine, like Windows, Linux, or Mac OS, and this website. So in the Zephyr official website, you can get a Getting Started guide to set the Zephyr RTOS environment on your machine. And also, you can download the project source code of this project we are presenting you in this URL. And so you can get software, you can change it, you can contribute it. Feel free to use it. So it's up to you what you do with it. So very important, ensure your downloaded project, which means the GNSS LoRaWAN tracker project, is located into your Zephyr RTOS environment folder, which means per default in Zephyr project / Zephyr folder, okay? Giving some features of this GNSS LoRaWAN tracker we are talking about, it is a GPS / GNSS tracker using S32W room. It obviously it can get the coordinates, latitude and longitude, and also it monitors the ignition input from the board. So it simulates a vehicle. So when you turn the vehicle on, it can get the input, the ignition input, we turn it off, and so on. As connectivity, it uses LoRaWAN by using a LoRaWAN module. It's manufactured by a smart modular manufacturer, okay? Controlled by AT commands using a WART interface. We'll see more about a little later. Regarding what this project does is it periodically sends the coordinates, latitude and longitude, and also in the same package, it sends a tracker status byte, where bit 0 means ignition status, which is 0 for off, 1 for on. Bit 1 has the GNSS fixed status, which is very important to determine if the coordinates you are getting is reliable or not. And I'm not using another 6 bits in the byte. So from bit 2 to bit 7, it's reserved. Now it's demo time. Let's check how code works. I'm opening the code here, the full source code in Visual Studio Code. Okay, so I will start by the boards folder. As I said before, boards folder contains all the DTO files or DTO overlay files that must describe the hardware for each target you are using. In this project, we are using only one target, which is S32W room. But if you have more targets, you can describe their DTO files into this folder, boards folder. Well, this file starts by defining some aliases, okay, to GNSS, to lead 0, which is a briefing light, a light that periodically blinks, indicating this embedded software is working, okay. And the ignition, which here is interpreted as a button, okay? So Zephyr RTOS sees the ignition as a button, okay? And you can see it here in the buttons node, okay? Ignition is described as an input key 1 button, and it's using GPIO4 from S32W room. It's pulled up and active low, and it's labeled its ignition signal, okay? So to sum up, Zephyr RTOS will see this as a button. Regarding the LED, the briefing light LED, it's wired to GPIO 18, it's active high, and its label is briefing light, okay? So its LED, it has only one purpose, blink when software is working, okay? Now let's start the UART definitions, which means the communication to the GNSS module, which uses an NMEA2 protocol, and by using a UART interface. So UART1 from ESP32 double room is used to communicate to this GNSS module here. And I'm using as TX pin the GPIO 25 and RX pin the GPIO 26. Okay, and for communicate to the LoRaWAN module, as I said before, via AT commands and UART interface, I'm using UART2 from S32 double room and GPIOs 23 and GPIO 5 as TX and RX. Still regarding the UARTs, okay, I defined its baud rates and in these nodes here, WART1 and WART2, and also for GNSS module, there's a special sub-node here into the WART1 node that defines which driver should handle the data received from WART1, which is the GNSS NMEA generic driver. So everything that comes from WART1 coming from the GNSS module will automatically handled by the GNSS NMEA generic driver. And so it can export the needed files and the needed control status and so on to read the GNSS or GPS module coordinates and status. Well, the first file to get deeper to is the main.c file, which is here in this project, the first .c file that should be run. Okay, so on its main function, it's very, very straightforward. All it does is to start every module here in the software, which means briefing light module, ignition monitor module, LoRaWAN module, and GSS manager module. And if some of these modules doesn't work or doesn't start or present some error, the log error message is presented, or a message indicating it's all good is presented. The simplest module here is the briefing light. Everything it does is blink light every time defined in this macro, which is 1 second. So from second to second, the light, the LED wired to the briefing light pin, it's turned it on and turned it off. It's too good. And this is done by a thread, okay, Zephyr thread, which is created using a K thread, and their parameterizations like priority and so on, it's defined to a kconfig file, which we'll see a little later. And another important part here is that the informations from LED, it's loaded from is directly from the DTO files by using this macro here. So when you declare a GPIO DT spec and use this macro, it will read from the DTO file for your target, which is the LED 0 underscore node alias, which means LED 0 alias. So in this line, the compiler goes back to the DTO file, try to locate a LED 0 node and load its parameterization here into this variable. Okay, so that's why the DTO file is interpreted during the compile time, not during dynamic by the boot time. Moving on software, here I have the ignition monitor, which monitors the ignition status and check if it's on or off, and also applies debouncing routines to register the right ignition on and off without bouncing on off all the time. So it uses a K timer, which is a timer, software timer from kernel here, And when the ignition status changes from 0 to 1 or 1 to 0, ignition level, sorry, it starts a timer. And if the timer reaches its end without being restarted, it means the bounce it's over. So when it happens, it calls this callback, and by this callback, I can get the uptime, the timestamp now, or uptime when it has been detected, and reading the pin, the ignition pin, to get its final state. So after bouncing, if its final state is 1, it means the ignition is on. By after the timer time gets ended and the ignition level is 0 or low, it means the ignition is off, and goes on. Okay, so the ignition monitor module init, it starts the ignition GPIO, it configures and everything as said in DTO file, and from this point on, everything is done by interrupts. Here, proceeding to the software, we have the LoRaWAN UART module, which handles this Smart Modular LoRaWAN module. In this module, as I said before, is Smart Modular LoRaWAN module uses UART communication, okay, using AT commands. So every function here that handles that exchange data with this module, it's in fact formatting and sending and receiving AT commands. Okay, so we'll get into a little later, but everything it does is to format an AT command and send and get its response. So the initialization of the LoRaWAN module is nothing but running every single command here to send the AT commands to start, wake up the module, set the LoRaWAN credentials, the join mode, and so on, everything regarding LoRaWAN, and also getting it ready to work. But if you see a little deeper, everything it does is to format AT command and send it using LoRaWAN UART. And if you can check this function here, the function that sent the AT command, everything it does, it just send the command, and there's a function to receive response for modular LoRaWAN module. So it's very straightforward. Moving on to our last module here is the GNSS Manager module, which handles all the GNSS messages received and already parsed from ENIMEA protocol by using the callbacks. So everything that comes from GPS and GNSS module is read by the GNSS driver, as we said in DTO file explanation before, and the driver parses all the data and raises the callbacks. So when the callback here is called, it gets the parsed data by this GNSS underscore data struct. So what I need to do is to check if there's a fix in GPS, and if so, I can adjust the latitude and longitude value by dividing it by this constant, indicating in the logs that it has a fix. And this value here, less latitude, less longitude, these variables are global variables here in this software. So I can access it in another function and get the less latitude and less longitude read from GNSS and GPS module. So after the initializations, everything is handled by a thread, okay, as a dedicated thread. And in this case, every second, the this loop is running in the GNS thread and checking the last latitude and last longitude that it has been read. And it sends it to the LoRaWAN module by using this function, send tracking data. So the LoRaWAN can send it to the cloud. Correction, this time is the uptime, the time that a position or a packet is sent from this device to LoRaWAN. In this case, it's set to 15 minutes. So every 15 minutes, the last latitude, last longitude, and ignition status are get and sent to the clouds via LoRaWAN. As I said before, the kconfig here looks very like in the Linux environment. If you develop Linux environment solutions, you recognize it. So it's very, very straightforward. And every config here can be accessed, it can be obtained or read into each module and so on. The CMake list file has no mystery too. The only point of attention here is to not forget to declare or to use each source file you need to build. Okay, so these are the main.c file plus each module .c file. And I will show you after you send it to the clouds, you'll have a 9 bytes chunk of data package, and which the 4 first bytes refer to latitude, the 4 next bytes refer to longitude, and the last byte refer to the ignition status in fixed status. In this case, fixed status is 1, okay, GPS is okay, and ignition status is 0. Just to be clear, this one is here is the fixed status, and this last bit 0, and the last 0 is the ignition status of this example package. Okay, so if you can check here in the terminal, I will restart the application. I have this project wire here. So Zephyr started. It's configuring LoRaWAN module. It already sees 11 satellites here, and it has a fix. And every 15 minutes or 900,000 milliseconds, it sends the coordinates and also the ignition status to the cloud. I will change the ignition status here. As you can see, ignition is off. I changed it again, ignition is on. It's already debounced, so everything works as expected. So as we finish the demo, I would like to show you the references used for make this presentation, which are the Zephyr project website, Zephyr RTOS GitHub repository, and block diagram get from the NXP documentation, and also some embedded LabWorks slides from embedded Linux course, as you can see in this URL. I would like to thank you all for watching this presentation. I hope it was helpful. And if you have some questions, please reach me at Q&A session. See ya.
And we are back to another Q&A session. And I am Pedro, and I would like to invite Pedro to join us to this Q&A session. How are you today, Pedro?
Hi, I'm fine. Thanks, Pedro. It's a little weird, Pedro calling Pedro, but it's okay.
Yeah, it's a lot of Pedros. Yeah, all right. So thank you so much for your talk. I know how much time you spend to prepare and get ready for sure for this Q&A session. So thank you so much.
You're welcome. I would like to thank you for the opportunity to be a speaker in this event. It's very, very important for me.
Actually, it's your second time here. Is that right?
Yeah, that's right. I was presenting a talk about Fuota firmware update over there in last year, DevCon24.
All right, and looking forward to see you at DevCon25.
Oh, I hope so.
Yeah. All right, Pedro. So first question. Besides changing compilation command, what are the necessary steps to port an embedded software to another target, other ESP32 SoC, for example?
All right. First of all, you need to check if your desired target is supported in Zephyr RTOS. You can do this by checking the board or ARC folders in the Zephyr RTOS GitHub. So you'll have a bigger picture of what's supported there. If your target is supported there, means you can port your software to this SOC. Obviously, you also need to check if your target has all the peripherals that are needed for your software. But this is an implicit if you want to port from a target to another. So ignoring this for a while, you need to check if your target is supported. Then, besides that, you need to prepare your device tree overlay, as I said in the presentation, in order to make sure everything you will use is declared or enabled in device tree. So Zephyr can link everything together and your application can access hardware peripherals and hardware resources.
I see. And talking about device trees, the second question is related. So does device tree work the same way it works in embedded Linux systems?
Oh, nice question. Yes and no. The yes part is the syntax and the nodes writing and the language itself, quoting, for device tree is the same. But there's a main difference in when device tree overlays are kicked in. In Linux-based systems, common Linux-based systems, you compile the device tree overlay or device tree files into a DTBO file, which means a binary or the binary object from device tree. And during the boot time, Linux will interpret bootloader will interpret this device tree device tree the binary object, and then passes to the kernel everything it needs to start interacting with this hardware. So in Linux systems, it does this work with device tree in running time. But in Zephyr, most of these operations are verified and done in compile time. So if something gets wrong, or if you write something wrong in a node, for instance, Zephyr can get this error, can catch the situation on compile time. So in my opinion, it helps a lot, because most of the common errors you can see when writing and using device trees can be solved or detected in compile time, saving time for us developers.
I see. Thank you. And I think there are a lot of people watching us they don't have any idea on how to get started with Zephyr, or even they don't have the tricks and tips for how to get started. So then the question I have here is, which are the main attention points when developing embedded software using Zephyr RTOS?
Right. I would like to summarize this answer in just one sentence to be clear. It's not try not to reinventing the wheel. Zephyr has a lot of already prepared subsystems for a great sort of things. Everything you can imagine, there's a module, a driver, or something there prepared to use. So the first main attention point is check in the Zephyr already prepared modules, drivers, and so on, to check if you have the right module or the module you need, and use it. Don't be afraid to use it. It's there for you to use. So, for example, if you want to get the GPS or GNSS information, there's a module right there that interprets the EMEA protocol, gets the information, the data from UART, parses it, and does everything. So you don't need to write it again. So by using these modules or drivers already prepared for you, you save time and you ensure you are using something tested and validated, which is a very, very good thing for embedded software product. So to summarize it all, I would say try not to reinvent the wheel. Check if there's something like something already done that you can just get and adapt. So you save time, you avoid headaches, and you surely will have a very, very modularized system.
Thank you very much, Pedro. I'm pretty sure that people will listen to you and try to not reinvent the wheels, because it's very nice to hear from someone with experience as you have. Pedro, I see no more questions here in the chat, but I'd like to thank you for being here, for giving your talk, and as well answering the questions here at the live Q&A. Thank you.
Okay, I would like to thank you very much for the opportunity to be here as a speaker. And if someone that's watching me now want to ask me something after, please feel free to reach me by email or LinkedIn or anything else you can find about me and ask me. I would be glad to answer your questions and talk to you about embedded systems. So thank you very much.
Perfect. Thank you so much, Pedro. And now back to the studio.
Thank you, Pedro and little Pedro, for that wonderful evaluation of Zephyr on ESP32. Folks, I would like to remind you that your feedback is extremely valuable for us, and we really appreciate it. And this year, we will be going the extra mile to thank you for your feedback. If you fill the feedback form, we will pick 5 people at random who will win a dev kit from Espressif. So keep that feedback coming in.
We'll take a short break now. See you all in 10 minutes.
Welcome back to Espressif DevCon24, Day 3. We have had some really engaging talks from our community members so far, and we have more coming up. Let me remind you to like this stream and subscribe to our YouTube channel. And I would encourage you to ask questions and share comments in the live chat. So Sergey, shall we introduce our next speaker?
Sure, Sudeep. Coming up next is Matej Suchanek, the CTO of Spectoda, who will take us through his journey of transforming lighting solutions with ESP chips and making it cool. So, let's get started. Light it up, Matej.
Okay, so welcome. Welcome to my presentation where I would like to show you what we are up to in Spectoda. First, I would like to tell you some kind of like a dream or backstory how it all started. So I was dreaming about this universal controller that would create some kind of like light installations I was thinking about. And what kind of installations, you ask? Installations like, for example, for 3D printers, if they print, they will show the states of the printing. So if there's some kind of problem, it will be then it will be blink. It will be blinking in red. Or some kind of installations where there will be drummers, and the drummers will drum to the drums, and sensors will pick up this drumming, and interactive animation will be showing all the drums at the same time wirelessly. Or I would like to create these cool spaces with fractal animations flowing through this space, and like this interactive installations for DJs, interactive ceilings or fences, and also like battery-controlled products that can synchronize wirelessly and create some kind of animations. And with this, I was thinking about creating like events where there will be like a story, animation, some kind of fun with this. Also, I would like to create create a system for controlling lights to this like industry or sports hall installation kind of stuff. Yeah, so like this warehouses or the sports hall and things like this. And in the extreme, create this interactive facades or like buildings that will monitor or like show some kind of cool things. So this is how it all started. This was my dreams, and I realized that I need to create some kind of serverless, this decentralized solution running directly on the ESPs for this interactive LED control, because this interactive LED installations are of many sizes. Yeah, they are really small. If you, for example, have one kind of lamp and you want this one lamp to interact with some kind of application or things like this, then it's only the lamp. Or in the case of the big building, it is really big, so you need to like scale it up. So with this, that's what we did. What we did in Spectoda, and now I would like to show you how it all works. So first, to this example of the sports hall. Yeah, you have in Spectoda we have basically two components. First is an app, and then there is a controller. The controller then can have many like variants or like shapes or sizes. For example, this is the controller for controlling this industry DALI controlled light sources, and this is controller with integrated like push buttons to control stuff. And with this building blocks, you can create wireless mesh installations. So here, this is like the hall. Yeah, you have the lights, and each row of lights has its own controllers. And on the walls are these switches. And the switches and the controllers each have ESP32 built in inside. And every controller with every other controller is communicating with over ESP-NOW in this mesh configuration like a network. And then there is this application that connects via Bluetooth to the nearest controller. And as the application is connected via Bluetooth to the controller, then the application can access all other controllers via the ESP-NOW. So this installation is local. Yeah, it works by its own. If, for example, half of the installation is without power or something happened to it, then the other half always works, because as the computing is decentralized between the ESPs, then there is no like single point of failure. So that's really cool. And with this approach, you can scale it from the really small application with only one ESP controller to really big installation, because as the number of controllers increase, then the compute also increase. So you can like scale it up with ease. And the second example about the building, we created this interactive light facade with many controllers, and this works in the same way. So the only difference is that you have controllers on the facade that do not control daily lights, like the simple like dimming, but every controller has connected addressable LED strips, and each controller then not only controls the intensity of the brightness as it is in the sports hall, but also generates animations. And this generating animations, the decentrally, in a decentralized way, in a way that this whole facade will show this one thing, is the core of the problematics we are working on in the software. So if you want to create animations, you need to render stuff decentralizedly on the controllers in a way that each controller is synchronized with the state of this like decentralized network. Yeah, so that's the problematics. All this is set up in this Spectra Studio. It is software we are developing with the intent of creating these light installations. And now I would like to show you all how it works. So with this, I would like to start in the simple example. Imagine that we have like this 8 sticks, 8 battery-powered devices that are standing on the podium, and as these players are playing, microphone is picking up the sound, and then some kind of animation is showing on the LED sticks. So that's exactly what I have here in this simulation. This is like the 8 LED strips connected to a controller. So here is the first one. So like this one. It has this S1 ESP controller, and the controller has this one port connected to it with 300 LEDs, and that's the thing you see here. And this simulated installation is then connected. Here you can see I'm connected to this installation with this studio project I have here. And with this project, I can interact with this simulated installation. So then how I can like create animations for this installation. In the core, every animation needs to be algorithmic. Yeah. So with this algorithmic approach, we developed this way of like puzzle pieces to create the animations. Yeah. So for example, I can like define here that from some kind of from the time 0, yeah, from the start of the animation to infinity. Yeah. So this infinity, I want to show solid color red. So I have like this simple instructions, and I can upload the instructions to this installation, and then every controller receives the instructions and shows red for the infinity of time. Yeah. Okay. Like this. Or if I switch to green, then there is this green. But I don't need to stick to this solid color. I can like create animations, yeah, because animations, that's what we like. So for example, I have like this simple animations of shot. I can switch to for example, this blue color, and if I click upload and then I unpause the timeline, yeah, then I will see that each LED strip shows this blue shot running from the start to the end in the 5 seconds interval. Yeah. Then if I shorten this interval to 1 second and I click upload, then it is faster. If I make the size bigger, then the shot is bigger, and if I change the color, then the shot is different color. And with these puzzle pieces, I have the power to create really complicated animations, because I can like snap it together in a way that it is complicated. Yeah. So for example, I will make this shot to be not so fast, and then if I disable this block, then it's like not showing here, and I can have like this rainbow cycle animation that looks like this, and I can combine these two animations in a way that if I combine it like this, yeah, so I have shot and then I add to this rainbow cycle to it, I have like this weird mashup of the shot of the white shot running across the rainbow. But if I swap this to scale, so or like this, it's more. Then I have like this rainbow background, and as the masks in Photoshop are combined are combined, then I can combine this animation to create like this more complex animation of rainbow shot. Yeah, so in this way I can like combine the puzzle pieces together to create stuff. So if I go back to this example, I can create this animation with this loading bar. Yeah, like this loading. This loading is like animation that loads one color to another. And if I snap this animation to this layer. Yes, I was telling you about the layers in the Photoshop. Then I can apply some kind of modifiers to this layer. So for example, I want to freeze this animation in 1 second. Yeah, so this set time sets the time of this animation to 1 second. So it will be freezed like this. And if I freeze it in different time, then this animation will like behave differently. So then I can create a variable. Yeah, for example, like this time of freeze. Yeah, I can take this variable and paste it here. And if I write some kind of like 2 seconds to this variable, it works in the same way as the 2 seconds would be here. And with this variable, I can create some like live control. Yeah, for example, like slider here. I will name the slider like position. Yeah, position. Okay. And with the slider position, I can send the value of the slider to this variable and this variable to this set time. So now with this slider, if I switch it to timestamp, I can like set the time 2 seconds, and then this will show. So if I then tell that is from 0 seconds to 5 seconds, yeah, like this. Then if I move the slider, then the animation moves. So then if I don't if I like forget about the slider and connect it to a hardware microphone, and then the microphone is moving with the slider, then this interactive installation is showing this animation of moving the bar up and down. Yeah, so in this way, you can create really complex and interactive animations if you want. So one animation I have prepared here. So this is like a really big project where I have this preview, this simulated installation of the facade I showed. And this facade has all of these simulated controllers. So here is like controller V1188, and yeah, like many controllers. And with this many controllers, I have this like big project. And if I hit upload, then the project is compiled, is sent to this simulated installation, and then this preview shows the way that it would look on the real thing. And you may ask, how is it all possible? And that's possible thanks to WebAssembly, because the firmware I have written in C++ for the ESP can be compiled or transpiled into WebAssembly, and this WebAssembly can then be run here in this browser. So every like this simulated controller is the instance of the WebAssembly C++ code that is running on the real ESPs. And as the ESPs are like sharing the comments and projects, uploads and things like this wirelessly in this mesh network, here is only like simulated. So it's like also like communicating between the simulated controllers, but it's a simulation. And With this WebAssembly, I can like be sure that what shows in the WebAssembly also shows on the real stuff, because every bug that is in the real firmware will show here in the WebAssembly. So this is like the logs that are that would be shown on the ESP console here. Here the same things. So with this system, Spectra, we are working on this way of creating installations in different way that is normally thought about or thinking about. Because normally you have like this server that is controlling some kind of like gateways, and the gateways are then controlling the satellite controllers. That's the stuff we are not wanting to like no. So that's not how we work. We work that all the satellite controllers have like piece of the server inside of them, and then we are making these tools like the app, the hardware, the firmware, the studio, and the cloud tools to wirelessly service all of this stuff. We are making it to create this different paradigm of creating installations for everyone. So if you want to help us create this crazy ecosystem of tools, we are right now looking for new projects we can like develop this system on. We are looking for funding, and we are looking for you, the people who are want to talk about with us. So if you look for if you look on our website, the spectra.com, you can find a Discord server, and you can come and say hi, and we can talk about the nerdy stuff. So my name is Maciej Schanek, and I thank you for watching this presentation to the end. And if you have some kind of questions, do not hesitate to go on our Discord server. Thank you.
And here we are for another Q&A session. And I would like to invite Matej to join us for this Q&A. Hey, how are you today, Matej?
Hello, I'm a little bit warm, but good. Thank you for inviting me.
Yeah, it's our pleasure. So first of all, thank you so much for your talk. I know you guys for a while, and I really like your solutions for it's as you can see, like, or actually how as our viewers can see, you have a very nice background. I think I will ask something similar for next year DevCon, because it looks really nice. All right, so we have a couple of questions here, and are you prepared for the questions?
Yeah, let's go.
All right. So the first question is, how do you ensure the reliability and scalability of the distributed wireless network for large lighting installations, especially in environments with significant interference or obstacles?
That's a really good question, and I think that it needs to be three things. First, the communication between the ESP needs to be as much broadcast as possible. So like to take advantage of flooding and take advantage of the wireless as it works, because wireless is broadcast first. And second, to ensure that minimum data is flowing between the controllers at any given time. So with our system, you create the project, that's the big amount of data. You upload to the network once, and with this big data, as many the bytes are shared, as many as possible are shared between the devices. So this big upload is done only once, and when it works in the production, there is only small like events and synchronized packets that are transmitted between the devices, and as many of them are shared with as many controllers as we can. So with this, we can like ensure that even if there is some kind of like frequency or things like this, disrupting the signal, it will always go through because it is small packets, so it works.
I see, and I imagine that you have tried several times before having like the, I'd say, final solution and the solution that just works.
Yeah. And I find that if you put ESP-NOW into the LoRa, the long range mode with the 5K encoding or something like this, it works really well. And even the ESPs with the PCB antenna are really good at transmitting the small packets that we need. So it works great.
Yeah. So thank you. So the second question is, how do you optimize the energy consumption of ESP devices in lighting systems, both during operation and in low power states, while maintain like responsiveness?
Short question, I don't. I rely on the fact that the lights are plugged into the socket, and the lights itself draw many times more energy than the ESPs. So I just have the ESPs on full throttle to 40 megahertz with always on the receiving circuitry and antenna. So it draws watt and a half of power, but I don't care. So that's what I do.
Yeah, it makes sense.
Yeah.
All right. Third and last question. How does your system handle firmware versioning and rollback in case of failed over-the-air updates across a distributed network of ESP nodes?
That's a really good question. Our topology is really simple. It's very flat. You have only ESPs, and the ESPs are each ESP is a master. Yeah, so you don't have one like a server that is connected to the ESPs, but every ESP is connected to another ESP. Then we have only ESP32s, so you can have one firmware uploaded to one ESP, and the ESP can copy its firmware to its neighbors, and with this distribute the firmware through the network. So you can even if you make the OTA update and some ESPs are unreachable because they are powered off or something like this, if you power them on, they will compare the timestamps. They will see, you have newer firmware than me, so it will request the firmware update, and it will peer-to-peer over ESP-NOW shuffle the firmware to the ESP. And then I have this boot check that runs the initial setup from the config. It tries to render one frame, and if it succeeds, then it's I check the OTA flag, and no rollback will occur. But if it crashes during this time, it will automatically reload back, or yeah, it will reload back to the firmware and try again.
I see. You do the most critical things first, and then after that, you make sure that if it passed or if it's the firmware is up to that point, then everything is fine, and then you can accept that firmware version.
Yeah, for me, it's really, I need that all the hardware has the same ESP, so this kind of things works. If I would have like ESP32s and ESP32Ss, then the firmware binary is different, so this kind of like sharing resources is not possible. So like this, yeah.
I see. So I don't see any question here in the chat. So if anyone else has questions, we will let you know, and then you can answer later, or people can get in touch with you. So Matej, I would like to thank you for your talk and being here to answer the questions.
I also like to thank you for having me, and have a great day.
Thank you. And now back to the studio.
Thank you, Pedro. Thank you, Matej. Sudeep, let me ask you, what you were doing when you were 16 years old?
When I was 16 years old, I think the only purpose I had in life was to annoy my parents, play around the whole day, and do nothing significant.
And what if I'll tell you that our next speaker is 16 years old, and at his age, he is doing drones with ESP32 chips?
I would be amazed.
So, let me amaze you and our audience. Please give a special welcome to Matej David Andracek, who is going to show us his work with drones that he built for his school.
Hello, my name is Matej David Andracek. I'm a high school student, and today I will talk about my project, the Drone Payload Release Mechanism, a device for dropping things. This presentation will consist of 6 parts. Background, where I'll tell you what the project does and its use cases. Requirements, where I'll give you some bullet points about what it needs to be able to handle. The receiver and the controller, where I'll individually explain the 2 most important parts of the project. Alternative modes, which I'll show you later. And code explanation, where I'll try to explain the code of the project. So first part, background. What is it? The drone payload release mechanism is a drone attachment that drops items from height. It is usually used to test track resistance, communication range, and parachutes of other small devices, such as small rockets, satellites, transceivers, and things like that. The drone payload release mechanism was created for a team at my high school who specializes in creating devices such as small rockets, parachutes, and satellites. Second part, requirements. What it needs to be able to do. There are 2 main parts of the drone payload release mechanism. The receiver, which is the main part that is attached to the drone and drops the payload, and the controller, which communicates with the receiver and controls it. The receiver must be able to lift up to 500 grams, because that is usually the upper weight limit of most of the projects that are tested or created by the team. It has to be lightweight, so we don't strain the drone and make it more or less controllable. And it has to be secure, which means we have to get the payload under control, or the payload or the tested project. So we cannot drop it unless we want it to. The controller must be easy to use. It has to prevent accidental activation, so again, the payload doesn't release unless we want it to, and it has to have reliable connection to the receiver. Third part, the receiver. The receiver is the most important part of the drone payload release mechanism. It uses ESP32 as its microcontroller, and it directly controls the release mechanism. It is attached to a drone, which enables it to fly and to drop our payload from various heights. We can also estimate its current height by using built-in barometric pressure sensor. It consists of two main parts, the power management circuit and the release mechanism. The power management circuit manages powering of the whole receiver. It consists of three main active parts: the battery charger module, the step-up boost converter, and the battery itself. It is a lithium polymer 3.7 volt battery. The battery charging module manages charging and discharging of the battery, as well as protecting it from overcharge, over discharge, and short circuits. And the step-up boost converter converts the voltage from 3.7 volts of most lithium polymer batteries to 5 volts. Now, we could technically convert the voltage to just 3.3 volts, which would be sufficient for the ESP32, but since we want to power components other than the ESP32 as well, we need to convert the voltage to 5 volts. The release mechanism is mainly made of 3D printed parts and a servo motor, and its main purpose is to carry and drop the payload. There are actually two versions or designs of the release mechanism: the slide ball design and the rotating hook design. The slide ball design is harder to manufacture, but can bear more weight, and the rotating hook design is easier to create but cannot bear as much weight because all of the load is applied to the axle of the servo, which can snap easily and break off. You can see the main support beam of the receiver is 3D printed from PETG, as well as the compartment for the electronics where most of the electronics beside the servo motor are mounted. You can also see there are two mounting holes on the two sides of the support beam, which are there so we can attach the receiver to the drone. Fourth part, the controller, the primary user interface. So the controller is the primary user interface to the receiver. It is also based on ESP32, and it communicates with the receiver wirelessly through ESP-NOW protocol. It is powered through USB-C cable, which can be connected into any 5 volt power source, for example into a power bank. Its two main parts are the main circuit and the button board. The main circuit is the most important part of the controller. It contains all of the most essential parts, for example the ESP32, most of the wiring, and the OLED display, and it is built on a breadboard, which makes it easily modifiable. The breadboard is attached to a glove from which it can be removed, because the breadboard is attached to the glove by using an elastic band, which is sewed to the glove on one side and held by metal pin on the other side. So if we remove the metal pin, we can slide the main circuit out of the glove. The reason the main circuit or the controller is built around the glove is I wanted to create a controller that is hard to lose, so you physically cannot lose it unless you remove the glove, and to make it non-intrusive, so when you wear it, it doesn't interfere with your other work. For example, when you're carrying something and you have the controller on, it should not impair your ability to carry something. On the other side of the controller, there is a button board, which is sewed to the palm side of the glove permanently, so it cannot be removed unless you undo the stitches. It contains 4 push buttons, one for each finger, and it is built on a custom etched PCB. It is connected to the main circuit with 5 wires, 4 wires for each of the buttons, and 1 extra wire which is connected to the 5 volt rail. You can see the button board is slightly skewed, and the reason for that is ergonomics, which makes it easier to press. I would also like to point out that in real life the button board is covered in this sort of padding, which makes it more comfortable to press, but I removed the padding on this picture so you can see the buttons themselves. The controller has a variety of possible interface elements. The two main interface elements are the button board on the back and the OLED on the front and the OLED display on the back. The additional possible interface elements are the gyroscope and accelerometer, which can tell if you tilt or move your hand, the flex sensor, which can tell how much you bend your fingers, and the buzzer, which can or an LED, which can notify the user once certain criteria are met, for example, when the drone reaches certain height. The reason you cannot see the last three on these images, nor they are built on the real controller, is that there's simply no use for them in the drone payload release mechanism. So even though they are possible, they are not used. Last thing I would like to mention about the controller is its screen. It tells you 6 different kinds of information, one in 6 lines. So starting from the top left, first line is the reach indicator. It tells you if the receiver and the controller are in reach. We know that by sending a message through ESP-NOW to the receiver and waiting for a response. If we receive a response, that means the receiver and the controller are in reach. If we don't receive a response, that means the receiver is either turned off or out of range. On the second line, you have the refresh timer. The refresh timer is kind of a loading bar that runs in a loop indefinitely. It tells us when the screen of the controller is refreshed. So even though the controller, the main CPU, runs at much higher frequency, we are limiting the frame rate of the OLED display of the screen, so quickly changing data are easier to read. The third line is callback frequency, which is one of few pieces of information sent to us by the receiver. It tells us the frequency at which data packets are sent. So if we have frequency 30 times per minute, that means we reach 1 packet of information each 2 seconds. It can be set on the receiver, which I'll show you later. I would like to mention that third line and second line are somewhat related, and one can affect the other. On the fourth line, you have pressure on the receiver, which is another piece of information we receive from the receiver. It's more precisely is the data that it receives from the barometric pressure sensor. And the fifth line is error line. This line displays all of the errors, either when they're from the controller or when they're received from the receiver. So for example, if the barometric pressure sensor on the receiver, which is connected to the receiver through I2C, stops working or is not present, the receiver sends an error message to the controller, which displays it to the user. The last line is a vertical one, and it is on the right of the screen. It contains 4 characters, either underscores or hashtags, and these 4 characters represents 4 buttons on the button board. So each one of those characters represents 1 button if it's either its press state or unpressed state. We display the button states in this way, so if the button board breaks or malfunctions, we know it before, for example, we accidentally drop the payload. So you could say it's kind of a safety measure. Fifth part. Alternative modes, secondary controlling modes. So what are they? Alternative modes alter workings of some part of the drone payload release mechanism, mainly its code. They are designed to aid in certain situations. They can be thought of as some kind of accessibility settings. There are 2 alternative modes, light sensor mode for the receiver and serial control mode for the controller. First, the light sensor mode. What is it? So, normally, when we want to drop the payload, we have to send command from the controller to the receiver, and if the receiver receives it, it drops the payload. But when the receiver has light sensor mode activated, instead of waiting for a command from the controller, it drops the payload when it detects that the flashlight of the drone has been activated. It checks for that by having a photoresistor, which is an electrical part that changes its electrical resistance based on how much light hits it. And we have this part mounted next to the flashlight of the drone, which enables us to tell if it's been lit or not. The main advantage of this approach, of this alternative mode, is that it doesn't require the controller to exist, because we control both the drone and the flashlight of the drone, and thus the release mechanism, from the same exact remote. which also means they have the same exact range. Because in normal mode, we sometimes can encounter a problem that the range of the ESP-NOW can be slightly smaller than the range of the drone, which can lead to some issues. But this alternative mode requires additional electronics, mainly the photoresistor to detect the flashlight and some part to cover the photoresistor, so other light sources don't interrupt with our flashlight detection. It also requires the flashlight feature to be present on the drone, obviously. Although this flashlight feature nowadays isn't that rare, it also isn't very common in lower price range of the drones. Another small disadvantage is that we cannot receive any data from the receiver because there's nothing to receive them with if we don't have the controller. Also, the ESP-NOW is not activated when light sensor mode is in use. So we cannot both have light sensor mode and ESP-NOW activated. Second alternative mode is serial control mode. So, normally you use the controller by wearing it on your hand, pressing the buttons on the button board and reading output from the display. But if for some reason the user cannot use the controller normally, for example they have two big hands, they can use serial control mode by connecting their controller to a computer, and if this happens, the controller effectively becomes an interface between the serial monitor and the receiver. It works somewhat like a CMD program in Windows operating systems. We send commands by typing and we receive our output by reading from the serial monitor. The main advantage of this approach is that people that cannot use the controller normally can use the controller. Another advantage is that it has a smaller chance of accidental activation, so because it's much more difficult to accidentally write a command than to accidentally press a button. And it also enables data logging, which means saving the data to our computer by just saving log from serial monitor, which enables us, for example, to calculate how much time we spent in the air or the speed of the drone. But it requires the controller to be connected to a device with serial monitor, which is usually either a computer or a notebook, which can be somewhat impractical to carry around in field. Sixth part, code explanation. Inner logic of the drone payload release mechanism. In this part, I will try to explain how the code of both the receiver and the controller works by using flowcharts, which should make it easy to understand. I would also like to point out that the flowcharts are somewhat simplified, and some information, for example delays, initializations, or some more complicated logic will not be displayed here and will only be explained by me verbally, or not at all. So, let's start with the receiver. At the start, which means when we power the receiver, it checks if light sensor mode is activated. If it is, we go to the lower path, which will start in the light sensor mode, which will turn us into the loop of light sensor mode. If light sensor mode is not activated, we will enter the upper path, which will lead us to the normal mode loop. Let's start with the normal mode. So when light sensor mode is not activated, we will firstly try to initialize communication with the controller, which means we will send a message to it and wait for a callback from it or some kind of response. If we don't receive any response, after a while we'll wait and try again. We do this over and over until we receive a proper response from the controller. This means that the controller is up and running and we can enter the main loop and start waiting for any commands from it. So at the start of the loop, we firstly check if we received any commands from the receiver. If we received any commands from the receiver, we will check if we received command to change the frequency. If we did receive command to change the frequency, we will change the frequency by cycling through a list of preset frequencies, and after that, we will send data from the pressure sensor, current frequency to the controller. We send data from the pressure sensor and current frequency always at the end of the loop. And then after that, we go back to the start of the loop. So, if we didn't receive command to change the frequency, but we received command to drop the payload, we will drop the payload wait a while, reset the release mechanism, because when we drop the payload, we open the release mechanism, and when we reset the release mechanism, we close it back up. And after that, we will send data from the pressure sensor, our current frequency, and maybe a confirmation to the controller that we dropped the payload, and go back to the start of the loop. If we didn't receive command to drop the payload, if we didn't receive any commands to drop anything or to change the frequency, we'll just send data from the pressure sensor and current frequency back to the controller and go back to the start of the loop. This loop runs forever, so it doesn't end unless you cut it from power, cut the ESP from power. This is fact for every loop I will be explaining, for every main loop. So let's go back to the start of the flowchart, and let's say this time the light sensor mode is activated. So if it is, it will lead us to the main loop of the light sensor mode. At the start of the loop, we check if flashlight of the drone is activated. If it isn't, we'll wait and check again. If it is, we will drop the payload, open the release mechanism, wait a while, reset the release mechanism, and after that we enter in this sort of loop. Now, if this loop wasn't there and the flashlight was on, the code would run indefinitely, so it would keep opening and closing the payload, the release mechanism, even though we turn the flashlight on just once. This loop, which checks if flashlight has been turned off, and not letting us continue until has been turned off, prevents that. So when you turn the flashlight on, we will run through the loop once and then wait until the flashlight has been turned off again, until we can go back to the start of the loop. This is for the receiver. This is code of the receiver. Now let's head to the code of the controller, which is somewhat more complex. At the start, we also have to decide if we start in normal mode or controller's alternative mode, which this time is serial control mode. We decide by checking if serial monitor is connected. Let's say it isn't. If it isn't, we start in normal mode and enter the normal mode loop. At the start of the loop, we read button inputs from the button board. And after that, we will check if payload release button is held down. If it is, we will check if it has already been held down for 3 consecutive seconds. If it isn't, we'll go back to the start of the loop. If it was, we will send a command to release the payload and go back to the start of the loop. If payload release button is not held down, we will check if frequency change button is held down. If it is, we will send command to the receiver to change the frequency and go back to the start of the loop. If neither of these buttons are held down, we will check if we received any new data from the receiver, for example, new information from the barometric pressure sensor or something like that. If we did receive any new usable data, we will redraw the screen with our new data and go back to the start of the loop. If we didn't receive any new data, that means the receiver is either offline or we just didn't receive any data. In that case, we just go back to the start of the loop without doing anything. Now, let's go back to the start of the flowchart, and let's say the serial monitor is connected. If it is, that means we start in serial control mode, and enter the serial control mode loop. At the start of the loop, we'll check if we received any new commands from the serial monitor. They have to be new. If we received the payload release command, we will forward that command to the receiver. If we received command to change the frequency, we will forward that command to the receiver. If we didn't receive any command, we will check if we didn't receive any command from the serial monitor. These 2 commands are from the serial monitor from the user. Then we check if we received any new data from the receiver. So if the receiver has sent us any new information, for example, new information from the barometric pressure sensor. If we did receive any data from the barometric pressure sensor, we will format that data and print them out to the serial monitor for user to see, to view. If we didn't receive any command either from the serial monitor or from the receiver, we will just go back to the start of the loop without doing anything. This is the code of the controller. And this is about my presentation. I hope you enjoyed it, and thank you for watching.
and we are here back to another Q&A session. And I'd like to invite the speaker to join me and answer the questions. Hi, Matei. How are you today?
Hello, I'm good.
Thank you. So first of all, thank you so much for your talk. It's very inspiring, and I think you will inspire a lot of people, especially the ones that are, I'd say, quite afraid of starting a new project, especially projects, quite complex projects like yours. So thanks for your talk. We have a couple of questions here, and the first question we select for you is, how did you came up with this idea?
Well, in the presentation, I told you the project is created for a school. It was actually, at my school, there's a team that would create rockets, satellites, and similar things. And I'm part of it, and we were preparing for a CANSAT competition, which is a competition in which you create these devices called CANSATs, which is like a satellite, size of a can, the regular can. It has a lot of sensors, and it sends data, it measures to your home base. You collect that data, and then you create a presentation out of them, which you present to live audience. And they had purpose-made new parachute for their CANSAT. So they wanted some way to test it out before going on the main event. So they asked someone to create a device which enabled them to drop their CANSAT from height on their drone. So I voted to do it, and that's basically how I started doing the project.
I see. And the project process, or the question here is, what was the process of building your solution? Like, how did you did it?
Well, first thing, I wanted to make some good. I wanted a good way to drop the payload, the CANSAT, and I took a lot of paper and drew out different mechanisms that could work, but more importantly, mechanisms that could receive our command to drop them. So I made a lot of sketches and even some prototypes. And due to voting of other team members, we settled on this very design. We had a lot of ways to drop the payload. We had timer, which was somewhat dangerous because it was unresponsible. It was not very responsible, and it had its flaws. We had also the light sensor mode, which was originally the only mode, but a lot of drones don't have this flashlight feature. So it ended being added as just only a side option or alternative mode. And then we settled on this ESP-NOW protocol because it is easy to work with somewhat. It also it is able to reconnect if we lose if we lose the connection. So that's what I ended with.
Perfect. And during the process, were there any challenges you faced when using ESP32, especially for this project?
Well, there weren't many challenges. The only challenge was actually building it together and making the communication smooth, because there was some things that got in the way. For example, the drone not responding to me was quite a challenge because for some reason the ESP kept shutting down. Then I figured out it was because of the powering brick or the powering segment. But other than that, it was quite without errors. I didn't encounter any major errors other than that.
All right. And what you like to improve or add to your project in the future?
Well, I would definitely like to add better enclosure, because the 3D printed enclosure you saw in the presentation is not quite optimized. And it also works on the drone that we used. So want to make it more universal so you can use it on other drones. And the second part is the controller, because actually mainly the case of it also because the glove was actually it was not the last resort, but I've actually tried creating regular kind of controllers, but they failed for multiple reasons. So I had to turn back to the glove controller because it is easy to make and it's also too easy to edit. So it enabled me to tinker with it and modify it without having to physically do a lot of modifications to the box.
I see. And to finish, is there anything you'd like to say to young people like you to inspire them or somehow motivate them to do projects like yours?
Well, I would say that it is a good time to start whenever you get hands on any kind of microcontroller. And even if you don't have anything, you can find a lot of simulators online which can simulate this microcontroller. There's the only thing I would say it's a language barrier because everything is English, but if you understand me, you can understand most of them. So I
Yeah.
would say to get your hands on some items, on some resistors, some LEDs, which can even be removed from some older devices. And do not be afraid of it. It can help a lot in a lot of certain situations and can be also be fun.
Perfect. So thank you so much. And I'm pretty sure that this talk will be very useful for a lot of people. Again, thank you for being here.
Well, I also am glad to be here and thank you for giving me this opportunity to present something.
My pleasure. So now we can go back to the studio.
Thank you, folks. I'm sure Matej has inspired us all to dream big and achieve everything we set our minds to. Now we'll continue focusing on education and how we can make learning curve for embedded development less steep.
Exactly, Sergey. Our next speaker is Omar Hiari, an educator, academic, blogger who is passionate about redefining the learning experience in embedded development. Omar's work focuses on bridging the gap between the complexity of Rust and embedded systems, making it accessible to learners of all levels.
If you're curious about how education and embedded system can come together, this talk is for you. Over to you, Amar.
Hello, and thank you for tuning in to my talk today. I'm going to be talking about redefining embedded learning with ESP and Rust. So I'm going to start with a little bit about myself, followed with embedded learning and where I see probably a significant gap nowadays in the learning process of embedded systems and even combined with Rust. Then looking at potentials of closing the gaps and what the ESP ecosystem actually provides us in order to achieve that. So a little bit about myself. I'm currently in academia and computer engineering in particular. However, I come also from an industry background, particularly in automotive embedded systems. I've been focusing on Rust for a little bit over 2 years now, in which I focused particularly on embedded Rust education. And during that phase, I founded the Embedded Rustition newsletter and also blog. I'm also the author of 2 books, which are Wire World and Simplified Embedded Rust. So a little bit about Simplified Embedded Rust. This is a book of 2 editions that is actually based on the ESP32C3 device and combined with the Rust programming language. And it was mainly a reflection of what I encounter in teaching embedded systems and what I encountered in learning embedded systems with Rust. So I'll touch more on this later, as a lot of this talk relates to what my thoughts were about creating that book. So starting with embedded learning. We as educators, ideally students that come into a certain field to learn, they would have some level of curiosity about this field. And our duty is to nurture this curiosity to help them find their passion. So along the lines of, well, embedded Rust, given that it's also an open source project, if the passion that these learners find or the learners find would be in embedded Rust, it would help towards increasing adoption and help the project grow. So in a way, also maybe finding their passion quicker is another way to put it, given that if they do not really reflect on a certain field, then we don't have to keep them there for long. So when we look at curiosity in terms of learning, it's often split into 4 stages. So the first 2 stages have more to do with procedural knowledge, where students rely more on lecturer or teacher to help them through these phases. And the latter 2 have more to do with self-knowledge, in the sense that students become more independent, relying on their own capabilities to get through the remainder of the process. So starting with each one of these, at the process phase, typically what this entails is providing students with the different tools and frameworks or that they would need for learning. And well, in a way, it's a phase that helps orient them into what is required to learn the content that is coming up. So in the second stage, that's where the actual content is delivered. And this is where the, let's say, teacher or lecturer's duty is to provide quality content to help them learn the material properly and quickly. And a transfer stage, that's where students start relying more on their own capabilities or the knowledge that they acquired to potentially solve questions or do mini projects. And then finally, in the self phase, this is where we would expect that students reflect more on the material that they learned and potentially discovered whether this is their passion or not. This is the phase that ultimately we'd like to get students to as fast as possible. So in my own experience, I would say that there's mainly 2 categories or types of learners along those stages. So on the right side, there's the type of student that is already probably in the field and has already reflected on a certain material or a certain field, and they just want to acquire new knowledge in a similar field. So they would be there to sort of go through those stages and acquire the associated knowledge with the additional part that they want to add to their knowledge within an existing field. However, the second type is typically the type that is curious but doesn't know much about a certain field. So this is the type of student that, as an educator, probably we would have to invest more time into keeping them excited, so we can get them to a stage where they can actually find their passion or see if the topic itself is their passion. So if we look at these stages along with excitement levels with time, so an ideal case would be something like this, where excitement keeps on growing with time until students find their passion, and this is sort of the highest level of excitement. However, this is typically not a linear line. It has its ups and downs, but the idea is that the trend is a growing one. Now, if we look at a traditional embedded learning process, typically in the early stages, we ask students of things like this, where they would need to choose and acquire hardware. They would have to wire this hardware, set up some tool chains, IDE choices, even frameworks for that matter. Only then, when we transfer to a content stage, that we start transferring knowledge and doing some coding. So students might have seen some of that early on, but it wouldn't have been something that they can do much with, given the level of knowledge that they acquired at that point, which is not much. So maybe they would run a Blinky example to make sure that their hardware is working, or experiment with other small snippets, but nothing more than that. And then in a transfer stage, that's when students will start exercising with examples on their own or solving problems, maybe even mini projects and labs. And finally, in a self stage, this is when they actually potentially do their own projects within a group or on their own. So what I often encounter with this type of approach is something like this. And I think many of us that are in the embedded world can relate to this in terms of what potential frustrations you can run into and doing all of these initial setups, or even choosing the framework or even hardware that you want to deal with. And the thing about it is, what is sort of an issue here for somebody that is new to the field is that they might run into issues without having enough knowledge to be able to fix those issues. So frustration builds up fairly quickly. And this is the impression that they build up about embedded, when it's not necessarily the case. Because for the most part, if you manage to set up a proper framework for yourself, you can use it for a while without having to change much. So if we compare this to learning programming languages nowadays, and from a learning curve perspective, learning programming languages, you can become really proficient fairly quickly, given that nowadays probably the first stage of process, all you need to do is open up a web page and you can start coding. You can go into a content stage almost immediately. However, as we've just seen, this is not necessarily always the case with embedded systems. And this is what I like to refer to as the embedded gap, in the sense that it takes longer to become proficient because of a lot of that work that has to be there ahead of time. So how do we close this gap? If we take a closer look, again, the challenges had to do mostly with hardware and software setup. So talking about hardware accessibility, whether it's in acquiring, choosing a particular hardware, the cost of the hardware, and then setting it up and wiring it, and which also implies knowledge about electronics. And then you have the part on the software end, which has to do with tool chains and software setup. And then we have, well, the ecosystem options and frameworks that students have to choose from. If we add on top of that the Rust challenge, so Rust itself as a language is often stereotyped as a language that is tough to learn. And most newcomers to embedded Rust would be more familiar with out-of-the-box Rust, which what I mean by that is the Rust based on the standard library, which has much more features and abstractions that one can utilize and doesn't necessarily require much low-level knowledge. And then additionally, Rust is an open source project, and much of the content in the field is frequent to change. So students would have to keep up with that as well. So in order to address the challenges, maybe one framework that already exists is the Arduino model, which makes hardware more accessible to use and provides a full solution of a hardware/software combination. However, I would say that even with that, there are issues that have to do sometimes with accessibility, or even hardware itself having issues, whether it's with drivers and so on, that students sometimes even run into. There is the part about the options, and this is more of an educator effort that would have to limit these options in terms of frameworks and ecosystem. But finally, my line of thought is more with shifting a lot of these things to a later stage of learning. But, well, the question is how? So if we look at the tasks that we talked about that are typically an issue, whether it's acquiring hardware, wiring hardware, tool chains, and IDE, the point is to take them towards a later stage. And the idea behind this is that, well, if we do this, what I had expressed earlier is that students typically have a higher level of excitement toward a later stage. And, well, probably at that point, they would have found their passion. So these type of things, other than having the knowledge to be able to push through them, it wouldn't be something that would frustrate a learner quickly, that would cause them to give up on the topic. So we can provide more focus on learning embedded or coding embedded without having to deal with any of these challenges. And then when the student becomes more comfortable and more excited, for that matter, we can introduce these things. Now, the question of how, there's probably two approaches, but the idea is that we provide alternatives for hardware and also pre-configured setups to students that they could just pick and start coding immediately, replicating the software experience or the programming language experience that I was expressing earlier. So there's two main approaches that probably exist in terms of solutions nowadays. So one of them is remote real hardware, and this is probably inspired by professional environments for debug, where you would have a pre-configured setup along with a camera, and you would connect remotely to this setup from home using an IDE, and you can tinker with that hardware remotely without having to change anything. You just have to connect to it. Another approach is simulators. So simulators in the context of CPU simulators probably have existed for a while, but here what I mean by simulators is more of a system simulator that includes a development board along with components that you can simulate or interact with. And within that context, to the extent of my knowledge, there's two solutions there, which are Walkwe and Tinkercad. So in terms of the ESP ecosystem, there's actually a unique combination that is available right now for beginners to use, which is Walkwe with ESP devices or boards and Rust. So Espressif, within their ecosystem, they provide official support for Rust on ESP devices and also for Rust on Walkwe. So you can actually spawn a simulation with several options of ESP devices. You can hook up components and you can start coding right away. Another part that is quite interesting from the ESP offering perspective is that it offers support both for the core library and the standard library. So earlier, as we expressed the Rust challenges, we said that most are familiar with out-of-the-box Rust, which is based on the standard library. So this option makes it more comfortable for those that are familiar with Rust, but not necessarily embedded systems and want to get into the space. So this is what the Walkwe webpage looks like. So you just have to open one and start coding. Now, this one doesn't have any components wired externally. So that would still be part where an educator would have to provide these pre-wired solutions. But again, there's still a lot that you can do even with the bare board itself without having to wire anything, especially functions that have to do with IoT. But again, the idea is that, well, all you have to do is spawn a web page and start coding, replicating programming language learning experience. So, sorry. So there is more that Walkwe offers. So it's not just a simulation environment. So if at a certain point you decide to connect hardware, you can flash immediately from a browser. You can actually even do local development if you want to. So with VS Code and JetBrains, there is support for Walkwe where you can actually do the simulation from your own IDE, or sorry, your own text editor. There are options for profiling, and what is also very interesting, there is IoT support. And by that, what I mean is that from the simulator, you can actually simulate the connection to Wi-Fi and interact with the internet or the cloud doing HTTP requests, and so on. So there is much more, which for those interested can discover on the WACWI website. So in conclusion, I think that there's a lot that is available right now from an embedded education perspective that different projects can benefit from in order to transform the embedded learning approach. And what is exciting right now is that along with languages like Rust that are open source, there is a lot of natural excitement around it that hopefully more let's say platforms can join a similar effort in providing such solutions for an educational perspective. And the idea is that, well, again, for any open source project, having a lot of contributors is obviously a huge benefit. And in order to increase adoption for a certain field, we need to remove the impediments for learning to help learners or people that are curious, if you will, get there quicker in hope that this would be their passion and finally contribute to the project. So just real quick, back to the book. As I mentioned, I'm going to touch back on it. So this is mainly what I had in mind when creating the both editions of this book. So it is a book that is self-contained in the sense that you can learn and do everything within the solutions or examples that are associated with the book, along with pre-wired examples with WACWI. So even for questions or exercises in the book, they are also pre-wired. So it helps streamline that process without having to spend much time, or any time for that matter, trying to figure out these things in order to start coding embedded software. So with Rust in particular. Additionally, because of the regular changes within the ecosystem, given that it's still dynamic in nature, there is or isn't a lot of stability just yet. So these books are regularly updated such that it keeps up with what is available right now in the ecosystem. So that's what all I had for today. Thank you for watching, and if there's any questions, please let me know.
And this was the last talk of the DevCon24. And now I'd like to invite Omar to join me for the Q&A. Hello, Omar. How are you today?
Good. Thank you, Pedro.
First of all, thank you so much for your talk. And I hope you will inspire a lot of people on how to learn embedded Rust. Thank you. We have two questions here, and I'd like to start with what challenges in embedded system education do you think can be overcome with embedded Rust?
So the nice thing about Rust, like I mentioned in the presentation, is that it's an open source project. So there's a lot of contributions that happen, and things evolve quite quickly. So at least from an embedded perspective, when it comes to learning, there's a lot that you can see from contributors that can add to essentially the whole project, if you will, to enhance the learning process. This is counter to potentially, let's say, other languages in the space, or that have been traditionally in the space, like C or C++. That yes, you do find material, but it's not open source. Well, not all of it, I would say, is open source in nature, and you don't find as many contributors, or you do not find as, let's say, much quick progress, I would say, compared to Rust itself. And the excitement around it itself is quite impressive.
I see. And just before moving to the next question, do you think that Rust somehow will motivate people to learn embedded system, or do you have something to say about how or if Rust can motivate people to move to embedded systems?
Actually, I think so, yes, because the thing about Rust, probably many know that it's been voted one of the most popular languages for a few years right after each other. But the point about that is that although probably those that enjoy or like Rust are not necessarily all in embedded, because of the focus on what it brings to embedded, it can attract, let's say, a community that is not necessarily involved in embedded, but because, well, Rust introduces probably a different perspective. So it's quite exciting in that part. And the thing about it that is also interesting is that you can, in a way, in some cases, like I had mentioned in the presentation, match the, let's say, experience that you have with developing Rust on regular devices or regular computers, not necessarily embedded ones. So it becomes, I think, quite attractive to at least try out, and maybe people will find it more interesting and get into, or have more people come into the space.
I see. And in your opinion, what are the challenges for the adoption of embedded Rust?
You mean in the industry or education?
Yeah, we can focus more in the education scenario, but if you want, you can extend a little bit for the commercial.
Right. So the education part, there's a combination of two things. So there is the toughness part of embedded itself, granted the things that we mentioned, but again, with the emergence of platforms like Walkway, it helps accelerate or eliminate a lot of those early hurdles. But then Rust itself is probably one of the languages that is famous for being hard to learn, or I would say takes or has a steeper learning curve. But still, at least my experience is that as you get into it, it's hard to get used to anything else. And well, maybe at least if there are more efforts that keep sort of pouring into easing both of those fields or both of these hurdles, you can come up with a combination that makes it more attractive to get into. Now on the industry side, at least in the embedded space, you're sort of contending with languages that have been there for tens, if not of years, and they're well established. So while Rust does bring a lot of advantages, its adoption is not going to be something that I would say happens within a very short term. It will take some time, but I think it has the traits that make it sort of prove that it's worth replacing traditional languages.
I see. So thank you. We have one comment on YouTube. Is basically about how to get the book. Someone is just asking, or if you can just paste the link.
Sure.
That would be great.
Sure.
Right.
Yeah. So it's serbook.com. So I'll comment on that. No worries.
All right. So I see no comments or questions here in the chat. So first of all, I'd like to thank you for being part of DevCon24 for your talk. And if you have any final consideration, you can go ahead.
Well, I'd like to thank you for giving me this opportunity. It was a nice experience. It's my first time, so thanks again.
Yeah, I hope you enjoyed. Thank you. And now we can go back to the studio.
Thank you, Amar. Thank you, Pedra. Wow, time flies, and this was the last talk of today and the whole conference. However, we still have plenty of your questions unanswered.
And as we promised, now we have our colleagues from Espressif, Anantraj Gupta, Technical Marketing Manager, and Ivan Rokhotkov, VP of Software Platforms with us. They will answer the most challenging questions that you left during the 3 days of the conference.
And if you still have your questions, please write them to the chat, and Pedro Menatel in our Q&A studio will make sure that no questions are left unanswered. So, Over to you guys.
And here we are, close to the end of DevCon24. But before we go, I would like to invite Ivan and Anant for the general Q&A. Hello, guys. How are you today? So I think we don't have Ivan audio.
Yeah.
1, 2, 3.
So I can't. Yeah, it's working. Thank you.
All right.
So how are you guys?
I'm good, Pedro. Can you hear me now?
Yes, now I can. Thank you. All right. And how about you, Anant?
Yeah, I'm good. Pretty excited.
Perfect. So it's really nice to have you guys here. So we have a couple of questions. And the first question is, kindly update what Espressif has done to help customers to meet the EU Cyber Resiliency Act.
Sure, I can take that up. So I think that's a pretty hot topic. We hear that coming a lot. Not just the EU Cyber Resilience Act, I would say it's also the US Cyber Labeling Scheme, which has come up, and a lot of other regulations coming across the world. So we identify that fairly well, and not just since the regulations come in. We have been focused on providing affordable security on our solutions since the very beginning, I would say. We did had a couple of talks during the DevCon, like the ESP IDF SBOM, which is a tool to scan dependencies and vulnerabilities of the project, and the ESP TEE, which is the trusted execution environment, which is equivalent to an ARM trust zone kind of a implementation. Apart from that, we have few of our products like the ESP32S3, which is PSA certified. We have ESP32C3, which is CLS ready, certified by the Singapore Cyber Security Association. So we have our product, and of course our other new chips will also get certified soon. That's in progress, I would say. So I think we are trying to help our customers be prepared for meeting the Cyber Resilience Act.
Thank you, Anant. The second question is, will Espressif invest into Rust like you did for C and C++?
Yeah, I can answer this one. The amount of work we do for Rust support will definitely grow as the adoption of Rust among our customer base grows. We are still right now in the early stages of this process. So we are focusing on things that are really essential, that we think it's key that Espressif does first. And this is mainly the ESP-NOW project and the related parts of Rust embedded ecosystem. The other thing I want to say here is that unlike C and C++ embedded development ecosystems, a lot of the things in Rust work the same or mostly the same way between embedded and desktop development. And there is just a lot less need to create embedded specific tools. The other thing is that due to the cargo package manager being such a core part of Rust, reuse of libraries is actually a lot easier in Rust, and there is a lot more libraries that work the same way for different MCUs, different chips. So there is just less need for silicon vendor like Espressif to create some things that we do have to create for C and C++ ecosystems.
All right, thank you, Ivan. Next question. What about Platform IO compared to Espressif IDE?
Right, so there are some things definitely are in common. If you develop specifically for Espressif chips, you will be able to create projects, edit your code, edit project configuration, run, do JTAG debugging, and so on, in both Espressif IDE and with Platform IO. There are some things that you probably will want to pick Platform IO for. For example, Platform IO supports chips other than ESP chips, right? And so if you work with projects that combine multiple MCUs, it might be more convenient than working with multiple vendor IDEs. You also, I think Platform IO has VS Code extension, maybe C-line plugins, so you have more choice between IDEs than with Espressif IDE. So Espressif IDE is aimed at a specific group of our customers who are familiar with Eclipse and would like to have that type of experience. And Platform IO is mostly oriented at another group, people who maybe are more interested in having similar experience between different MCU families. So I think it's both has its pros and cons.
Right. Thank you so much, Ivan. The next question is there news on ESP32 P4 mass production date?
Sure, I can take that. So definitely, we know there is already sampling the ESP32 P4. So you can have the evaluation board available for you through our official channel, which is on the AliExpress. And having said that, there are still a few limitations on that evaluation board yet, which are listed, mentioned on the page to purchase as well. We should be having the mass production very soon.
Okay, thank you, Anand. Next question. Is there a chip version with more IRAM? We always need to remove important parts from the IRAM or the code won't compile.
Okay, I can answer. I think the context of the question is related to the original ESP32 chip, and in the ESP32, the memory architecture was not really flexible. There was a certain hard split between IRAM and DRAM, so you would run into the limitation of maximum amount of IRAM you could use. We addressed this limitation, this problem in newer chips, so everything starting from ESP32S2 and later, so C3, C2, S3, and so on, they don't have that hard split between IRAM and DRAM, and you can use as much internal RAM for code as you like until you run out of space in the internal memory. So yeah, pretty much selecting any newer chip than the original ESP32 should solve this problem.
All right, thank you. And why don't you have a built-in LAN module by now?
Okay. So I believe if this question is about just the Mac support, we do have support on that on the ESP32 as well as now on the ESP32 P4. But if the question is regarding the PHY as well integrated, that's I would say it's not a very good economic sense to have that there because it increases the size pretty much, and yeah, that's majorly the reason we don't want to integrate the PHY as well on the module.
Okay, thank you, Anand. And the next question is a few words regarding ESP32 P4 regarding software side.
Right. ESP32P4 has, I think, been covered in several talks in DevCon. So different projects have added support or are in progress of adding support for ESP32P4. In general, software support is provided by ESP IDF, and one of the things we try to do in ESP IDF is to make sure that all the different chips, they are covered mostly by the same APIs. So if you have used a previous Espressif chip, let's say S3, then chances are that you will be able to take your program and make it work on P4 without a lot of modifications, just by changing the target. And we even tried to make it work for Wi-Fi. So P4 doesn't have Wi-Fi or wireless connectivity in general, but we have a solution where if you connect an ESP32C6, for example, to ESP32P4 over SDO interface, then you can call all the usual Wi-Fi APIs on the P4 side, and we will automatically take care of sending that data over and receiving the data from the connected C6. So C6 will act as a Wi-Fi modem essentially for the P4. So that is kind of the short version of what is the software support for P4. There are some details, like for instance, P4 has a lot of new peripherals that we just didn't have in the previous chips. Let's say maybe a camera, display, and several others. And of course, each of those will have its own new driver. So there will be also some new code. As for other projects, you heard about updates in Zephyr, our plans in Zephyr, which include P4, and we definitely will support P4 across the rest of our software projects like Arduino and others.
Thank you, Ivan. And still speaking about P4, the next question is, and if I remember correctly, it's related to WebRTC. But the question is video streaming application possible for the ESP32P4 standalone MIPI cam and or in combined with SDIO connected Wi-Fi MCU, for example, ESP32C6?
Yeah, so I can take that. So yeah, I think that's pretty much one of the major use cases which we believe for ESP32P4 to be used in as IP cameras with microcontrollers running the feed from the MIPI camera, doing the encoding in the microcontroller. So we do have an H.264 encoder in hardware, which can support up to 30 frames per second at a 720p resolution, which is pretty decent for a entry-level IP camera application. And then, yeah, you can use either the built-in Ethernet to do that transfer, or you could use an MCU connected like the C6 or the C5 in future to transfer it over Wi-Fi. So yeah, it's definitely possible. We do also have, I would say, examples to run the WebRTC as well as yeah, such use cases.
All right. So like just to remind that all the questions we answered so far, we picked it from the last days. So we do have some questions from today. And the next question is, what is the plan for Espressif systems for Africa and Ghana? There are a lot of developers using ESP boards here.
Yeah, so yeah, definitely right. I mean, we understand Africa is very important for us, and we know there are a lot of active developers there. I believe last year in November timeframe, we did had like 3 sessions in South Africa. That was with one of our distributor partners. We had a full ESP IDF roadshow. So definitely Africa is in our minds, and yeah, we will see how we can do to the other parts as well.
Thank you, Anand. And the next question is directly to you, Ivan. So will Espressif support Linux run on ESP32P4?
In all likelihood, we are not going to support this. It is technically possible. We have some internal tests about this, and we did run Linux on ESP32P4. However, this is what's known as no MMU Linux. And because ESP32P4 doesn't have the proper type of MMU that Linux kernel requires on RISC-V, it's possible to run Linux, but it's not really the same experience that you get with loading the applications and all the things you normally expect. So it's a flat image where everything is pre-flashed into the image, and you can't really modify it. But at the same time, as we saw, for example, on ESP32S3, and ESP32S3 was not even closely intended to run in Linux, and there were people in the community who made it possible. Max Filipov is the key person to mention. So maybe there will be people who will want to run P4 on Linux, and if it takes off, then of course we will do whatever is necessary from our side to make it easier.
All right. Thank you. So before we finish, I'd like to thank you, all the participants, all the audience that asked questions. And now I'd like to thank you, Eva and Anant, for being here answering the questions from not only from the previous days, but as well from today. Thank you.
Thanks, Pedro.
All right. So if you have nothing else to say to the audience, maybe we can finish the general Q&A. And maybe if there are more questions, we can answer later by chat.
Sure.
All right. Thank you. And now we can go back to the studio.
Thank you everyone for sticking around for that extended Q&A session. And thank you Pedro, Ivan and Anant for answering and for those detailed answers. It's been great to see so many tricky questions from all 3 days of the conference get answered.
Yes, and now we have come to the official close of Espressif DevCon24. It's been an amazing 3 days of sharing knowledge, learning new techniques, and seeing just how much our community has achieved. From keynotes to in-depth technical talks, every session was filled with something valuable. If you missed anything, don't worry, we'll upload each talk separately to YouTube soon.
We've seen some incredible projects made by drastically different areas by people of different backgrounds and mindsets. It is amazing to see the possibilities out there for developers of AI and IoT systems on Espressif platforms.
We would like to thank all our speakers for their time, expertise and dedication. And of course, thank each and every of you for joining the stream, asking questions, making comments and being such an engaged community. Your participation is what makes DevCon so special.
Before we wrap up, we want to take a moment to recognize the incredible effort that went into making Espressif DevCon24 a possibility. A huge thank you to our DevCon team who have been working tirelessly behind the scenes for almost 8 months starting in February, from planning to coordinating with speakers, handling logistics and making sure that everything runs smoothly during the live broadcast. None of this would have been possible without their dedication and hard work. A separate thanks to the documentation team who did the hard work of translating all the talks.
And special thanks to the digital marketing team in Espressif Shanghai who made the broadcast in China. And of course, huge thanks to our backstage team. The whole conference is made in-house and here is our production team. Wojtek Bartoszka, our director and producer. Andrzej Buchta, assistant director. Jan Prachaska, director of photography. Pedro Minatel, idea and concept creator and QA master.
It's been a pleasure to host you over the past 3 days, and we hope you're leaving with some new ideas and inspirations for your next project. We were your host, Ani, who helped us yesterday, Sergey,
and Sudeep. We can't wait to see what you create next. Goodbye and see you next time.